I'm going to get started now, folks. A warm welcome to the Large Language Models Bootcamp. This course is a 12-week course in which we do two things very thoroughly. We build enterprise class applications with language models. We do retrace pretty much all the major enterprise applications that dominate the industry at this moment, from semantic search to retrieval augmented generation, multimodals, code generation, and so forth. At the same time, we focus on the foundations. In this course, you'll notice that it is not just all code and projects and programming. It is also understanding the foundational ideas behind it. When we understand the foundational ideas, you will notice that for some things there are textbooks. For many other topics, there are no textbooks. When there are no textbooks, we will be relying on research papers. Paradoxically, in our field, unlike other fields, the research papers are written with great clarity. They're much easier to read and faster to make progress with than from some of the textbooks that are there, which can have errors and confusion sometimes. So we'll be relying a lot on some textbooks and also a lot of research papers in this course. We will be using a PyTorch and Transformer library and a lot of libraries for programming. We expect you to know Python. If you don't know Python, we also offer some remedial Python getting started sessions. You should reach out to the teaching assistants and they'll get you going with that. We'll be organizing that session soon. With that as a background, a few logistics. This course today's session is public. So it is a blend of a meetup sort of event as well as the first day of the course. Now, in deference to people who are here just to sample, just to get a flavor of what language models are, I will keep today somewhat light. Some of the technical depths will be kept for the second session. There is a joke I like to tell, and you may have heard me say that very often. A person happens to do equal amounts of good and evil. So when he dies, the bureaucracy up there cannot determine whether to send him to heaven or hell. So they ask him to sample. He goes to heaven, finds people praising God and being very serious. Then he goes to hell. Very interesting people, excellent coffee, as you can smell, and then good company. Right? It's fun there. So he comes back and says, I'll go to hell. The moment he goes back to hell, there is a devil waiting with a big stick. Temperature is high, coffee is cold, and he gets a beating. And he says, why? He says, well, yesterday you were a guest. Today, you're one of us. Right? So in the same spirit, today you guys are the guest. All serious stuff will start from the next session. With that caveat being there, we will get started. This course is comprised of some basic elements. I'll just mention it, and then we'll get started with the main matter. There will be every Saturday the main session. This session will have, it is focused on making sense and understanding the topic. That will be the primary driver. Every week, we'll take a new theme, new topic, cover it in depth. You will receive these handouts giving you a layout of what is being covered. What we expect you to carry away from this week as learning. There are many things we'll cover. You don't have to understand everything. You just have to understand the key takeaways. The point is, this audience is wide, and we want to cater to people who are just getting started with this field. At the same time, there are people in the audience who are already working with large language models and who are here to get a deeper understanding. So to cater to the needs of this fairly wide and divergent needs audience, what we will be doing is teaching from the beginning to pretty deep. But you have to pick your point at which you want to stop. It is not necessary, absolutely not necessary, to understand everything we teach in the very first go. But in the lesson plan will be mentioned the key takeaways. By end of the week, you need to just make sure that you have completely grasped the key takeaways. If you have not, then you need to put a little bit more effort, get in touch with the TAs and so forth. So that will be today, the Saturdays. It will have theory sessions, some code walkthroughs, some demos, some presentations in subsequent weeks of you guys as you present your project, the projects that you are doing with this knowledge. You'll be presenting to each other, getting peer feedback. That's that. Now, in this course, we have 10 teaching assistants. They are all AI engineers. They're high caliber people. At this moment, one of them, my peer, Chanda Lakshmi Narayan, Dr. Chanda Lakshmi Narayan, he is from one of the toppers from IIT and PhD from US in one of the hardest subjects. He leads all your labs, coding projects, everything. He's here in the audience. I'll let him introduce himself.
Hi everyone. Thanks for the introduction, Asif. Been very kind. So yes, I have. We have been with Support Vector since 2022, and yes, it's been a great uh, learning here because we keep doing R&D on new stuff all the time. Every course we learn as much from the students as we learn. We think we teach. So and I'm again looking forward to this journey here. This time we have a lot of new items planned also compared to the previous courses. From an introduction about me, I did my graduation, master's, and PhD from Syracuse University in physics. That was way back in 1995. So since then, I have been with, I would say, last 15 years I have spent in the AI/ML field. And I see that more and more AI/ML is becoming practically indistinguishable from physics. So yes, I am liking the place here. Thanks everyone for joining us.
Yeah, thank you, Chanda. So he leads all the TAs, AI engineers, because it's a weekend. At this moment, those AI engineers are not here. Otherwise, I would have loved to introduce them all to you. They are there. Please use them. This course, unlike Coursera or Udemy, etc., it is not about passing a lot of content to you through videos. It's about actually teaching you as in direct interaction. We love to talk to you. We love if you engage with us. If you get stuck at 3 in the night, you can reach out to us and somebody will get onto Zoom with you and help you through with your project. The only request we have is engage. You will learn the more you engage with us, the more you engage with the learning material. That's one. The second thing is we have a cluster, a fairly well-developed cluster. To learn AI properly, to learn language models properly, you need access to good hardware. It's not something you can do on the laptop. On laptops, the kind of exercises you can do are toy exercises. This bootcamp is about building genuine enterprise class products, hands-on, so that it is a quasi work experience. People come here and they go away with the experience that makes their subsequent job in AI feel easier than what they go through here. At the same time, we build you up from scratch. You don't have to feel stressed about it. So the cluster is a huge asset. If you try to do this homework in your cloud, any of the clouds, you would easily rake up $15,000 to $20,000 worth of bill. The fact that we have made it available to you absolutely as part of this course should speak to how much value you can get by actually engaging with the labs and the projects. I can't emphasize that enough. You won't get this opportunity, so much hardware to your accessible to you 24/7 for the whole duration of 3 months, free, other than your tuition. That is a resource that you should use to the maximal extent possible as a learning aid. The other thing you will get is, you see these rooms around you, they have no labels. Form teams, as you form teams, take one of the rooms. That room becomes yours for the duration of the next 3 months. You can hang out there, camp there, leave your stuff there. Don't leave very expensive stuff there, though. Or you might be the proud owner of lots of new laptops. So use those rooms to discuss, to learn, Collaborative learning is known in research to have a high impact. It really accelerates your learning when you learn from each other. Is the collective intelligence kicking in? Please do that. Those are the things you get. There will be 2 lab sessions every week besides the Saturday main session. The first lab session is about recap. You will, everything that we go through here, you will get extensive notes on the course portal. And yes, there is a very detailed course portal with a lot of resources available to you. Every lecture, everything we do is there. There's a lot of additional material. All the research papers are there. You will find the recaps of this pretty soon, typically in 24 hours on the course portal. You can read it, come having read it to the first lab. Nevertheless, Purnendu, one of the professors in our team, he will walk through the recap of everything we did here. This is just for you to mentally tick mark that, yes, I remember these things. It's also a time for you to ask questions. If something is not clear, you can ask. And then there is a quiz, self-assessment quiz. The quiz is not only of self-assessment value, it has another value because we spent about 20 in a day, 6 plus, 8, about 12 contact hours with you. It is per week. It turns out that that is not enough. There's a lot that we want to teach you, and we sneak it in all sorts of places, in our project specification hints, in our quizzes, in the answer to the questions, we put in extra learning for you. So do take the quiz simply to understand the nuances of the question and the answers. That is that. All the code segments in the lab will also be on the course portal. Now, this first lab, if you have a paucity of time or if it conflicts with your work schedule, it is something that you may not want to attend in person in that situations. It is advised that you attend, but not necessary. If you can't attend it in person, the recap, watch those videos asynchronously. Many people who are advanced, who understand everything in the main session, that is today, Saturday, they tend to do this. They will watch the videos at 1.5 or 2x the speed and pause only where they need to pause and slow down and listen to it more carefully. That from experience from the previous batches, people say that that proves to be very helpful to them. Do that, but please do the quiz anyway. The next lab, the second lab, is the main coding lab, in which the team has created a lot of good exercises to get you started. They will talk about the tools that are required, Hugging Face tools, trainers, models, etc., etc. They will talk about the trade-offs. Why did we pick this tool and not some other tool? What are the advantages and disadvantages? How should you use it in practice in the industry? Then they will take you through some use cases. We'll walk you through code. These codes are meant for you to study and get started. We'll walk you through the code. Then we'll leave you with some exercises. Do those exercises, please. In the very first lab, our team will take you through VPN access to the cluster. We'll show you how you can have your own VM. From the VM, you can connect your IDs, your VS Code, your cursor, whatever is your favorite ID, to connect to it in such a way that it looks as though you're coding locally, but in reality, behind your code is the full power of the cluster. Are we getting that? Those of you who are familiar with VS Code or Cursor know that you can SSH to a server. Your code base can be on the server, but it looks that it is local. You're coding locally with all the GUI loveliness, but when you run the code, it runs on the server. Use that facility, because many of the labs you won't be able to do on your laptop. They require powerful hardware. My team is going to take you through all of those exercises, and our head, the person to whom we are very thankful for setting up the entire cluster, is right here, Fan. He has set up the entire cluster for you, and it's a lot of hard work that we have been doing through the winter break to make all of this possible. So please do use it. At the same time, if you notice any glitches, let us know. Lastly, you will have a project, capstone projects. multiple capstone projects. We highly encourage you to do those projects. Projects is how you own all the knowledge we teach you. Otherwise, it will wash over you. Now, there are two tracks of people, leadership track, who only want to understand what is language model and how to use it in practice, how to do enterprise class projects. That audience may also want to do the project. To do the project doesn't mean to code, get down and code. It is just being part of a team and seeing how a solution is designed. Because at the end of it, you'll be in leadership roles, and your job would be to guide the team and give them advice on what is easy and what is hard. You get that insight by seeing how your team struggles to do the capstone project. Also, another word about coding. We are in 2026. Nobody codes by hand anymore, just as nobody does long arithmetic by hand. People use a calculator, it's a tool. It is not cheating to use a calculator in your tool, or it is not cheating for an accountant not to do a paper ledger books, but to use an Excel spreadsheet. In the same time, we live in a world in which the coding agents have become remarkably powerful. I encourage you to use the coding agents to do your assignments. That will make it very easy. It has democratized coding. Anyone can code now. But if you have coding experience, you have one added advantage. You actually understand what code the AI has written. And when you do understand, it's a little easier to steer it in the right direction. Think of it this way. These coding agents are giants of intellect. And you are steering the giants. That's what engineering has now become. It is no more hand coding, but it is steering this amazingly intelligent giants to the goal that you want to take them to. So take that approach to doing your labs. Are we clear, guys? So that is all that I want to say about the logistics. And with my apology to the people who are here in the meetup and would like me to get onto the matter at hand, let's do that immediately now. The topic of this bootcamp is large language models. So large sounds rather large. And what was large yesterday looks small today. If you have been following the trajectory of language models, you would realize that a few years ago, 200 million parameter model was considered large. GPT-2 was 175, or GPT-3 was 175 billion parameters. And that was huge, horrendous, couldn't be downloaded. Today, those are considered rather regular size models, and small models are still counted in billions. So large is an adjective, and it depends upon which year you are in that will determine the size of the model. Circa January 2026, the large models are of the size of 6 to 10 terabytes, or 6 to 10 trillion parameters, not terabyte, 6 to 10 trillion parameters. That's what's the size of the frontier models today. So large keeps getting bigger and bigger. So what we will do is we will not focus on the word large. Large is useful when you have an application or an idea and you want VC funding. You go to the VCs and say, I have a new language model. They'll yawn. But if you say, I have a large language model, it can do many, many things. Well, hopefully you'll walk away with large funding. So let's keep the large aside. We'll focus on language model. What is a language model? I would like to illustrate this with two demonstrations shortly. Let the reality convince us that machines now speak. They understand human language. Roughly speaking, machines have developed the ability to understand a language so well that they capture even the subtleties, not only what we said, but what was left unsaid. I'll repeat what I said. I'm saying machines have become so unusually primed to human language, unusually sensitive to it, or underst- they understand so much nuances of it that they not only understand that which you say, but that which you have left unsaid. It is a marvel that these things are possible. There is a statement by Arthur C. Clarke in his book. He said, a sufficiently advanced technology is indistinguishable from magic. What we see today, just for the common man outside the cabal of researchers, a small cabal of researchers, in 2022 also, most people would not have believed that these things that we see today was possible in our lifetimes. How many of you would agree with that? And yet these language models have broken upon the scene. ChatGPT was the poster child of this revolution. It had the highest adoption curve that we have ever seen. And the world would never be the same. But language models actually have existed for almost a decade before that. And today we are going to understand what they are. Today we'll take a big picture view rather than jumping straight into a lot of code and implementation and so forth. Let us step back and ask, for the rest of our life, how should we understand the word language models? What should it mean to us? It should mean something. And what should it mean? And I'm positing that language models are machines that understand human language and all its nuances. That's a big statement. Now, I'll give you guys a mental picture to carry in your head before we do the demos. And there are two demos that we will do. And I bet some of you who have been working with LLM would yawn and say, well, seen that, done that. Others will say, yes, it is remarkable. But look at it through the lens of a person in 2022, not from the lens of a person of today. And we'll walk through that. But let's ask this question, what is a language model? So imagine that your native tongue is, pick one, let's say English. You also happen to speak Mandarin. It's something that I've been trying to learn very unsuccessfully. When you are a kid, it's easier to learn. When you are my age, let's say, it's a difficult task. If you make 2 steps forward and 2 steps backward. You learn something, you remember it for a month, and then you realize that it's slipping away. But let's hypothesize that I pick up enough Mandarin to be conversational. Now, somebody speaks to me in Mandarin. What would be my mental reaction? Would my mind internally be reasoning over let's name this person as Alice. Alice talks to you in Mandarin. How would you respond internally in your mind? Would you be natively thinking in Mandarin in response to her? Or would you be translating it first to your native tongue? I would argue. You need to understand that exactly. Your first instinct would be to understand what Alice said. You would parse it, understand it. And whether you consciously realize or not, what you're doing is, here is Mandarin input. And your mind produces a private English English version of it, isn't it? And it might write it in its private diary. Now, that private diary may be a piece of paper that you heard, or more likely, it will be in your mind itself. You'll remember it in some scratch pad of your mind. This is what was said. Make sense? So this is your native tongue. And we tend to respond to other languages by understanding it in our native tongue. But how do we feel that our understanding is good? That which we understood is correct. What is its measure? That it captures faithfully with high fidelity that which was said in Mandarin. In other words, we want a faithful representation, high fidelity, capture. You want to have a high fidelity capture. You don't want to lose any part of it. Would that be a basic sine qua non, a basic requirement of your understanding? Now, let's put that in a language that is, I'll say that in a slightly different word that is a little more engineering, lossless semantic capture. You want the input to go through a lossless semantic capture when you capture it in English. Semantic means the meaning of it. Together? Otherwise, it is not that useful. The usefulness degrades the more lossy it is. Otherwise, it becomes a game of telephone that children play. You say something to a child, the child says that to the next child, to the next child, to the next child, and at the end of it, something absolutely different comes out. We all have experienced that. And we don't want that. We want a lossless semantic capture of the content. So this native tongue representation of what you got is important. The technical word for this is a language model. Okay? Let us throw some words now or vocabulary here. Latent representation. Latent representation. Latent means what? No. Latent means what? Hidden. See, this is manifest. But suppose I told you that behind this glass is a whole process of glass making that you can deduce. That glass making process is latent. You have to infer that. It's hidden in here. Only an expert can understand that. So the latent is the opposite of manifest. So latent, why do we call this a latent representation? Because this is what your mind understood in the native tongue. You don't speak it aloud. How would you know that that which you captured in your native tongue, the latent representation, is actually correct? There has to be a proof. The proof of the pudding has to be in the eating. One easy way could be, could you give it back to me? Say in Mandarin or in French or in English or in whatever language. Does that make sense? We can say, now, this latent representation, can you decode it based on what your purpose is? Let's say you can summarize it, you can translate it, translate to French, you can do a sentiment analysis, etc., etc. A lot of practical things. Or you could answer the question that was asked in Mandarin, answer in Mandarin, and continue the conversation. Would that be evidence that your understanding is correct? That you have a good latent representation? You can therefore quantify it, empirically measure the goodness of the understanding by having it do something, having the machine do something, or having a person do something, and then smile and tell whether your fluency with Mandarin so far is good enough or not. Is that what teachers do when you go and try to learn a new language? So that is it. This is called a sequence to sequence model, or architecture rather. This is a man, people use technical jargon, encoder, latent. Now I'm just going to translate it into language that you often find in textbooks. Decoder, output. So what are the observables? Empirically, what you see? Here is a machine. Input went in, output came out. Input is what? A sequence of tokens, a sequence of words. And what was the output? Again, a sequence of words. That is why such architectures are called sequence to, and this two is to being cute. It should have, you could sequence to sequence architectures. Some people also call it sequence to sequence models or sequence to sequence networks, etc. But you would agree that the core of it is this translation. You yourself are a sequence to sequence architecture. When you hear in Mandarin and respond in Mandarin with an answer, or translate it to French, or do any one of the other things, internally, whether you realize it or not, it's a two-step journey. First, understanding it in your native tongue, and then decoding that understanding into an answer, into an output. It turns out that machines can do that. But then you ask this question, what is the native tongue of machines? Is it English? After all, it's a very often spoken language. Is it French? Is it Mandarin? It turns out that machines don't speak our languages. They have a language of their own. And that language I will call machinese. Would that be a good name for its native language? So machines speak machinese, and this machinese represents itself as, of all things, points in space. People often call it vector, not exactly accurate. And the colloquial term used in engineering or AI literature is these are vectors. So we'll be sloppy slightly, and later on we'll refine this way of looking at it. Uh, people, you can take it by saying machines speak vectors, but they don't really. What they do is, do you see the globe there? It is the surface of a Earth. Where do we live? We live on the surface of the Earth. Now, imagine that we were little points. As far as the Earth is concerned, we are quite little, puny little points compared to the scale of the Earth. You're sitting there on the Earth, and what machines do is something exactly that. You say something, you say the cow jumped over the moon, and it says, ah, I got it. It puts a point somewhere on the surface of a hypersphere. Earth is a sphere, but you imagine a sphere of very high dimensions. Why high dimensions? There are technical reasons we'll go into, but for now, just think sphere, two-dimensional, like three-dimensional sphere, and so the surface is two dimensions. You put some latitude, some longitude, you put a point there, and you say, ah, this is what the user said. It contains the meaning of what was said. A point. Now, why a point? Why would you put it as a point? The reason is points have notions of proximity. When in human language I say something and you say something similar, then the machine can put those as 2 points close to each other on the globe. So imagine this. If you say something here and something else is said which is similar, let's say X, and something similar is said, it will place it nearby on the surface of the globe. On the other hand, if you say something very differently, this was cow jumped over the moon, and somebody says, machines learn through the process of gradient descent. Are the two related? No, not at all. And what machines do is something very interesting. They will take this, treat this as a North Pole, and they will actually put that irrelevant, completely different statement, as it will turn out, on a equatorial plane. If you think of this point as the North Pole, it will put it somewhere along the equatorial plane of it. Let's get this intuition right. Let's say that this is your X, and you say something completely unrelated. As you will see, machines will go put those points far, far away from this point. They tend to do that. It's just a very interesting phenomenon that leads to quite a few beautiful results. This subject of language models is machine actually living a geometrical life. It does geometrical actions. It's very fascinating. You can either read it through very complicated code, you can understand this subject either through lots of mathematics. How many of us feel intimidated opening a machine learning textbook? I always get scared. I feel it's a good time to go out hiking anytime I open such a book. Right? So, but I'm telling you, there is a far easier way and a very direct way to understand this field. Think geometry. This is all that machines do. They put two things, two pieces of text that mean something similar near each other, but they put things that are dissimilar, unrelated, far apart, almost orthogonal to each other. And that is all that happens. So if all that happens is, I can do that, now think about it this way. You have a whole corpus of knowledge, lots of text, lots of thoughts. Each thought belongs to a point in this globe. Then each neighborhood of thought is it's like a metropolis. Each subject, let's take the subject of, AI. It will be teeming with those points, all about AI, different aspects of AI. And they will be like a city populating a certain region on the globe. Does that make sense, guys? Right? Let's call it the metropolis of meanings. This whole globe behaves and shows, just as when you fly over, take a flight over in a plane, what do you see? You see the cities, lit up cities. And all the houses in the cities, all the things they together form the city. In the same way, if you think of these points as little specks of light, then it is like looking at the globe at night, looking at the landscape at night as you fly over it. And what do you see? You see these beautiful lit metropolises, cities. And each city is about something. This is about AI. This is about anthropology. This is about cardiology. This is about history. And that is why machines tend to like using points on a surface, in particular, points on a surface of a unit hypersphere, to represent a thought. The native language that it speaks are points. Are we getting the intuition? Any questions? I'm saying that every thought becomes a point on the surface, because points on a surface, they have notions of proximity to each other. And therefore, machine can know or handle similar thoughts by placing them close to each other, and dissimilar thoughts by placing them far from each other. Now what happens? What are the consequences of that? Thing very early on that people realized way back in 2018, and that will actually form the programming labs of this week. Just this idea, all that you have learned in the last 20 minutes, would you believe that it created a revolution in search? Search engines had existed since prehistoric times, in one way or the other. Think about it this way: human knowledge accretes. We as a species depend on knowledge. We don't have claws. I have no claws or horns. Right? So we have no survival skills other than knowledge passed on from the previous generation. But knowledge accretes and exponentially grows. To handle that knowledge, our ancestors made carvings on the cave walls. Then they started writing on papyrus leaves, on palm leaves, because knowledge grew even more. Then you had to keep track: where are the palm leaves, where are the papyrus leaves. And so in the great monasteries and libraries of the world, knowledge began to get gathered. Then people realized they need to index it. You would go to one of the first earliest recorded attempts was the Great Library of Alexandria in Egypt. They sent people to all civilizations of the world, picked up all their knowledge, scribed it, cataloged it, put it in the library. So you could go to a librarian in the Library of Alexandria and say, I want to learn about astronomy. And the librarian would say, oh, go to the third floor, the fifth aisle, look into this row, look, look on this shelf, and you'll find it. What did he give you? He gave you the coordinates of what you were looking for. Without those coordinates, you could not have meaningfully found that knowledge, because you can't do a linear search from the first book in the library to the last when you're looking for the book on astronomy. Is it obvious, guys? Now, that is indexing knowledge. From that, over time, grew the Dewey system of libraries, the modern Dewey system that you see on the spine of the library books, to catalog knowledge, to catalog books. And then out of the digital version of that became the search engines. They would maintain indices, keywords, and from the keywords you would go to the values, the actual locations. So keywords are an interesting way to look at it, and we'll dwell upon it in the later part. No. If you give it a piece of text, and so I'm deliberately being a little intuitive here, the question is, think of one thought as one atomic unit, semantic unit. There, Therefore, the question that you are really asking is, a text may have many thoughts, one leading to the next, to the next, to the next. And that brings up deeper implementation questions. How do you not throw in lots of thoughts and ask the machine to make it a point? Because machine, whatever text you give will make it a point. But let's be simple today as we start and think one atomic unit of thought. I had bananas for breakfast today, as one point, for simplicity. And it will get real pretty fast in the coming weeks, but for now, stay with the intuition. So the earliest search engines that people created and has been there till today goes like this. Google and everyone else, or your Elasticsearch and all of Bing and whatnot. Suppose you have 3 documents. The cow jumped over the moon. B, cows and ducks were in the meadow. And C, Apollo 11 landed on the moon. Now you see 3 documents, but imagine 300 million documents. It's just a matter of scaling the idea up. So what you would do is you would pick up the keywords cow, jump, moon, cow, duck, meadow, Apollo 11, land, moon. And you would create a table, cow, in which documents is it present? It's present in A, it's present in B. What about the word jump? It's present only in A, and duck is present in B, meadow in B, and Apollo 11, C, would be in C, and landed, and then we can do moon is the most crucial one. Moon is there in A and C. So suppose I gave you a search box, and the user happened to enter cow, moon. What would you think is the most relevant sentence or relevant document to pull forward? So cow happens to be there in A and B, and it happens to be in A and C. Right? So these two would be your search results. Does it make sense? These are your search results then. And thus the search engines that we had for decades. This is the kernel of the idea. What you're looking at is called inverted index. So when you use Elasticsearch, Solr, whatever it is doing, and you sort of take all your documents and index it, that's what your machine is doing. It's shredding it into its keywords and creating this inverted index table. After that, the second part of the journey is the retrieval. You give it cow, moon, it picks up the documents. But there is another part where a lot of thinking is required. How do you relevance rank the results? Let us assume that there are sophisticated algorithms that can relevance rank it. And that's where a lot of magic happens. To take this idea and to scale it up to planet scale data and planet scale search engines is a massive piece of engineering. It's formidable engineering. Nevertheless, the key idea remains this. And it remained this till 2018. But people realized that if we instead use this language models who tend to take whatever text you give and convert them into thought points on a unit, on a surface, they do better. Would you like to guess why they do better? A machine, a search engine, which uses a language model that converts a text into a thought point and if you use a language model like that to search, to build a search engine, it does much better than traditional keyword search engine. Most of the time, not always, most of the time. Can you guess why? Yeah, yeah. Guys, may I please request you one thing? On your table, you'll find microphones. And if you can just use the microphone, turn it on and speak into it, then remote people, the people who are on the Zoom, they also can hear your question. Otherwise, I'll have to repeat the question. Please say that again. Turn it on, please. Yeah. And a little bit closer to it.
Yeah, it points to the location in space where the search is so that it can just grab the things around it.
That is right. What you could do is, let's say that the user has a question. What do cows do? Is a question. That piece of text, if it becomes a thought point, where will the machine store it? On the surface of the globe. It is likely to store it next to, would you agree? It is likely to store it next to A and B. And so if you pick a few points in the neighborhood of that query, you will end up getting A and B as search results. Right? May I repeat that intuition? User has something to say or some information. You take that information, make it a point in this, on the surface, on the globe, and find its neighborhood points. Whatever text those points represent are really good search results, relevant search results, because they are semantically related, they are semantically similar. Would you agree with that intuition? Because irrelevant things are far away. So you have a search engine. So now we have two ways of making search engines. A keyword-based search engines, and this is called semantic search. Semantic search engines. I am claiming that for a large variety of situations, this is the superior way. Why is that? It understands the meaning, yes. What else? Say that again. It captures the context. Yes, very good. See,
Things which you have not asked also could be given.
right. See, I started this session today by saying language models are extraordinarily good at understanding us. They not only understand what you said, but also what you meant and left unsaid. Machines have something called a theory of the mind. Whenever you give it a text, you say something to a machine. And you can do this experiment and verify. To ChatGPT or to Gemini or to Claude, any of these frontier models or DeepSeek, say something, ask for some information, leave some typos in there. And sometimes don't ask for too clearly. Have you noticed that these things are extraordinarily good at inferring what you really meant? Anyone has had that experience? And it comes back and answers to you. But another thing you'll notice, it answers to you very differently than it answers to someone else. If it knows you from your wording, it can sense pretty much what you know and how to answer it. And it will give you a sort of a you appropriate answer always. Anybody has had that uncanny feeling that these machines seem to know you very well? They do. It turns out that for that you don't need a long history. Just give it a detailed question, input, prompt. It can infer that. It's the theory of the mind. It understands who you are and makes communication efficient. These machines can do that. Can just entering keywords and can a keyword search engine do that? It cannot do that. These machines understand what you really want. More importantly, language is ambiguous. When I search for the word bank, well, in Silicon Valley, the moment I say bank, everybody starts thinking about their financial bank accounts and smiling at the number sitting there. But bank may not just be financial. It could be a river bank. It may be your friend banking on you to bring the pizza on the visit. It could be a road banking when it curves. It could be an aeroplane banking to align with the runway. So the word bank, there is polysemy in it. Language has homonyms, polysemy. It has ambiguities. It has what we call endophora. It, it means, oh, I just used an endophoric term. What was I referring to? I was referring to the human language. But how do you know that? For that, you have to remember what I just said. In other words, it has back references, sometimes it has forward references. And when you read text, don't you come across this? As was clearly explained in equation 6.2 or section 4 point, chapter 4, section 2. Do you encounter those things, guys, in documents? That's antiphora. So language comes with all of that. Trouble is, given the richness of human language, a keyword is just not good enough. Would you agree? If you search for bank, it is a poor way of searching rather than saying, where is the nearest bank to, or what are the banks that I can go to deposit my money in Fremont? A natural language question. And what people found is that when you use language models, the search results get amplified. Doesn't mean you throw away keyword search, but you augment keyword search with a semantic search engine, and you get a hybrid search. And it's tremendously effective. In the demos that we will do, we will see that. Chinda, are you still there? Yeah. So
Yes,
what I
yes,
would
I'm
like
here.
to do,
I'm
what we
here.
would like to do at this stage is,
Are you able to hear me?
yeah, I can hear you. Chinda, we'll
Okay.
do this demo. We'll do two demonstrations of the power of language models. One, Chanda will show you, we will deliberately write something that I challenge you to decipher what it says and how many of you can interpret it. And then we'll see how what is the language model saying about it. So Chanda, would you like to please bring up that
Yeah,
image?
I can. I will do that. So I have two images. Which one should I show?
One at a time.
Okay. My screen is visible.
Oh, hang on. Yes, it is. Almost. Yes. Now it is fully visible. Give me a moment. I'll maximize here. Yes. So guys, may I ask you a question? Uh, I have absolutely no idea what all this weird thing is. Anybody understands what it says? It is almost like saying the horse of a horse is zero, for all we care. I have no idea what it means. And there's even an equation. This is exactly when you see things like this in, suppose you were to see things like this in AI textbooks or machine learning books, that's exactly when you would feel, okay, time to go for a hike. Right? But anybody would like to guess and interpret what it says? Hard, right? Let's give it to a language model and see what happens.
So here, this is a language model we have deployed on one of our servers.
By the way, it's running in the room right behind you.
So this is a vision language model. And this is the image that I just showed here and displayed in the Jupyter notebook as well. And we have given a prompt saying, I'm a physics student and came across this notes. Can you explain it? Put this explanation as a tutorial in a LaTeX document. And then we gave that image encoded in base 64. And it gave a very detailed explanation.
So let's look at the explanation. It says the boundary of a boundary is zero, a tutorial. Let's see if it understood it. In mathematics and physics, the statement boundary of a boundary is zero is a fundamental principle. Can you scroll?
1 second.
Up.
I went. Yeah. Yeah.
Is there also a markdown version below? Or
Yes, yes, below this.
that's good.
But actually, that markdown version also, we need to know because it became a LaTeX, right? So I think what I can do is, let me do one thing. We'll have to, right now,
It's
we
okay.
have
That's
to
okay.
make do with this.
We'll
Yeah.
just read this. Yeah, I'll just read this. So let's read this. In mathematics and physics, the statement the boundary of a boundary is zero is a fundamental principle that has deep implications, particularly in the context of vector calculus and electromagnetism. Oh gosh, how many of you remember those difficult subjects? This tutorial aims to explain this concept and its connection to the absence of magnetic monopoles. Oh, what does that mean? You know, if you take a magnet, do you notice that there's always a north and south? And if you break the magnet into two pieces, then what happens? You end up with two magnets, each having a north and south pole. But can you ever get a magnet with only a north pole? So it says that somehow it's related to that fact that magnets, they never come with only one pole. And it goes on to say mathematically the statement is this, here represents this, understanding the boundary operator to understand why boundary of a boundary, double boundary is 0, consider a simple example in 2 dimensions. Let M be a closed curve, a one-dimensional manifold in a plane. So you make a curve on a page. The boundary of M consists of the points on the curve itself. So you agree? You have a boundary. Now, if we take the boundary of this, we are essentially looking for the boundary of a set of points, which is an empty set. Complicated explanation, but what it means intuitively is, you see the sphere, guys? If Earth is solid, the surface is the boundary of it. Can you ever come to the edge of it? People used to believe there was an edge to Earth, the flat Earth theorist. But other than the flat Earth theorist, the rest of you, can you find the end? Can you find the ends of the Earth? Earth doesn't have ends. It doesn't have any boundary. Yeah. On the surface, there is no end. Right? So that is it. So that's what this thing is saying. And then it's saying, oh, that is somehow related to electromagnetism, a deep connection. Now, folks, what just happened? Imagine in 2022, with the lens of 2022, if you saw this, how many of you, honestly, would consider this magic, that machines could do this? 2 takeaways. Machines not only understood what was a cryptic piece of text, but it also has the civilizational knowledge within it to contextualize that knowledge, that contextualize this scribble. And remember, the scribble didn't come as beautiful text entered in a keyboard. It came as handwriting. So it has vision language understanding, vision understanding. Many things are going on here. It understands handwriting. It understands what was written there. It contextualizes it with the civilizational knowledge. And then the decoding part happened. It then explains what this cryptic piece of text is. There's a common statement that magic is everywhere. It's so commonplace we don't notice it. I hope you would agree that this is magic. Now we'll take another example.
That's
of an
below
image.
here.
Yeah. Let's just look at this image. How many of you look at this image and go, Chanda, can we just bring up the image without all the rest of the ID?
This one?
Yes. Open it.
Oh, you mean
In a
through
preview. In
the?
a preview.
Yeah. 1 second. I'll expand it a bit.
Yeah. So guys, let's look at this page. How many of you can enlighten me right at this time? What is this? Looks like this is exactly when you say it is Greek, because I can see Greek characters there, theta and eta and whatnot. And there's even a diagram there. So we'll ask the same question. Let's see what we ask the machine. Can you explain this diagram and the associated equation? I would like to have PyTorch code to implement this. Remember, we live in 2026 now. Writing code looks so antiquated. So let's see what happens. What can the machine do? Oh, look at the explanation. The diagram illustrates a 2D projection of a lost landscape in machine learning, lost landscape, etc. For how many of you know what lost landscapes are, guys? A bit of machine learning. Doesn't matter. So we will learn it in this course. Let's go down. And you go down. And to boot, the new way of writing code. Just hand scribble something, show it to the machine, and out comes the code for you. Does this not feel amazing? That is the power and the potential of language models. I would like to now show you, would you like to see another demonstration or this is enough? Let's see how well it understands emotions. And then we'll take a break.
I'll stop sharing.
So
You'll share it, right?
what if there is a
Yes, I'll share it.
unintended thing there which actually distract the machine to some knowledge space which we don't want?
Enlighten me a little bit more.
So
Say
if it's actually some mistake in understanding of like
oh, we should do that. Chanda, actually, please share your screen. And now let's introduce a mistake. Let's in the equation. Oh, but you'll have to do that. You'll have to make a picture and so forth. Can we take a
Yes,
picture in
yes.
which we introduce a mistake and see how well it, you'll be surprised. So while Chandra
I
is
mean,
doing that,
right now, this is a handwritten. I took a picture
no,
of
the
it.
second one, Chandra, the second one, in
Yeah.
that, just the theta, just make it theta square and turn the minus into a plus. And then in your prompt, just say, identify the errors and fix it too.
Okay. No, no. It will take me some time to do all that.
Yeah, that's what I'm saying. See if you can pull it off in a little bit. In the meanwhile, I'll continue teaching something else.
Okay. Fine.
Yeah. And only if you can pull it off, then we'll look at it. Huh? So,
Yeah.
all right, folks. So now I'm going to share.
what if that mistake actually really means something? I mean,
What do you mean by mistake meaning?
So you said like you make minus into plus and make it a square. Like what if it actually really exists?
It will analyze it. It will give every weightage to seeing what would it mean if this is true. It will give you an interpretation that way. For example, minus becoming plus becomes from a gradient descent to a hill climbing. It will say this is the equation of hill climbing. Then it will put it next to that image and say it does not seem appropriate to this image. Okay. And it will point out the contradiction. It's amazing what it can do. So, folks, I would like to show you something here. Where am I? Give me a moment, guys, and I will open recent workflows, fine-tuning, data science 1. Guys, do you, I noticed that some of you are getting a little, oh no, this is the wrong document. Give me a moment and then we'll do our break. But please stay with me for a couple of more moments. I'm going to show you something that is worth waiting for. Trust me, guys. It is semantic search. See, what I've done is this search that I was talking about, I'll just give you a sense of it. See, we said that there's a search query. Somehow the magic happens. The machine understands what it is. How does it understand? We'll figure that out. But it makes it a point and puts it on the globe, right? And then it finds nearest neighbors to it, and it all seems very abstract. The query becomes a point. You pick the nearest neighbors of that. Let's see what it means in real terms. There is a simple corpus of documents that we'll talk about, and let me go to that. Notebooks, examples. Imagine that the world is made up of such 16 documents. Or so, because I had to do this. All of this code will be yours, guys. It will be on the course portal. So don't have to worry about it. I took some poems, variety of documents. Obviously, my favorite is the Jabberwocky poem, Alice in Wonderland, The Looking Glass. It was brilliant. The reason I chose it is that machines can understand nonsensical language too. It was brilliant in the slithy toes, the gyre and gimble in the wave. Now, what did I just say? I have no idea. But that is it. And then some better text like Dickens, it was the best of times, the worst of times. Then many such passages, some about dogs, some things. Then Keats, then back propagation, attention, the topic that we learned today, etc., etc. And with these things, I did a search. When I do a search here, see what happens. First, you take all of these documents, each document becomes a point, right? So, and here's something worth reflecting on. Here is this text, the first one. It was brillig in the slithy toes, this poem. I could have taken any one. And it becomes this point in space represented as a vector, a high-dimensional vector. Now, how many of you can look at these numbers and say, obviously is the Jabberwocky poem? We can't. That asymmetry is the great paradox of our times. We have created machines that have an exquisite understanding of our language, of its nuances, of even things left unsaid. But we don't have any way to understand machinese except through geometry. Wouldn't you want to learn that? Isn't that asymmetric? They understand us so well. Shouldn't we try to understand how the machine thinks? That is what this course is about. And because if you can genuinely understand how the machine thinks, how it reasons, and it is geometric, you will be a far more empowered AI engineer than a person who is just copying code from tutorials and running it and just hacking their way through. Because that is flying blind. You're making random walks and hoping you'll reach your destination. You have no understanding what is where. That's the point. But we'll go down. We'll take a quote, a friendship with animals. I deliberately took a very difficult, deceptively simple, but difficult query. Guys, friendship is what? Is it a thing like this? No. Animal, yeah. Animals, I can see animals. You can't see friendship. A bit more abstract. And we search for it, and look at the search results that it came out with. What is noteworthy is what it chose to make the first search result. It says, golden retrievers are not bred to be guard dogs, and considering the size of their hearts and their irrepressible joy in life, they are less likely to bite than to bark, less likely to bark than to lick a hand in greeting. In spite of their size, they think they are lap dogs, and in spite of their being dogs, they think they are also human, and nearly every human they meet is just to have the potential to be a boon companion who might at any moment cry, let's go, and lead them on a great adventure. How many of you have golden retrievers or dogs? No dog owners? Okay. Jacked up tuition for you. No, sorry. If you're lucky, A golden retriever will come into your life, steal your heart, and change everything. I definitely concur with that. I had a golden retriever. But did you observe something interesting about these two first hits? Did you find the word friendship in the text? Did you find the word animal in the text? Both the keywords are missing. Isn't that remarkable? In fact, it is the third search result. If a man aspires towards a righteous life, his first act of abstinence is from injury to animals. Animal at least showed up. In a keyword search engine, would the first two results have showed up at all? But do you believe that the first two results belong there? How many of you feel? Because friendship is an emotion, it's a state, it's a feeling. The text, the first two texts, without saying that, are imbued with that emotion. And so the machine catches on to that which is unsaid, to the deeper meaning. That is magic. Let's go to the next one, visual search. Oh, what could this be? Now, this is a golden retriever, and golden retrievers are always smiling. It's a if you have one, you'll realize that it's smiling and it's looking at you. What are you up to now? But to the machine, when you feed this in, what are you feeding? You're feeding it 3 grids of numbers, red, blue, and green channel, floating point numbers. Now, when it goes into the machine, what does the machine understand? And you go and search your corpus and see what it comes out with as best search results. Oh, golden retrievers are little children as one of the search results. For the love of these furry dogs, a smiling dog. Did you realize it caught every characteristic of the picture it was looking at? Just reflect upon it. A decade ago, it was unimaginable that this could be done. You could search into images and ask it questions. And I want to show this to you before we take a break. Search. I again give it a hard query to love a dog. See, if you were to give it to a typical search engine, even with images and indexing, it would probably come back with heart shapes for love, right? And dog pictures. But see what a language model, what does a language machine come up with? How many of you feel that each of these pictures is quintessentially representative of a love of dogs? Raise your hand if you're impressed. Okay, half the class is unimpressed. All right. Isn't that awesome that they can do that? Likewise, and when you get this code, please put in your queries. Try it out. Play with it, please, in this session. Own this. Really explore the power of language models by changing the queries. Today is simple. All you have to do is change the queries and see what response it comes up with. And in the lab that Chanda showed, replace that picture with any handwritten scribbles of your own and do that. You can even handwrite things or give it code sections, pictures of code sections with a bug, and it will spot the bug and fix it for you. That's the world we live in. It says, a house near a lake. This is interesting. There are many houses near a lake. They can be ugly houses. Right? They can be industrial boxes next to a dirty lake. But when we say a house near a lake, besides the literal meaning, what else do we mean? We all dream of having a vacation or a house next in a right next to a lake, don't we? It brings us pictures of idyllic beauty and isolation. Does it? So let's see the pictures that it brings up. By the way, this is searching through a vast corpus of tens of thousands of pictures. and picking these ones out. Do you think it caught both the literal meaning and the subtext, the cultural subtext? Yes. Yes. So you can search for it, explore it. When you get this lab, just explore it. All you have to do is change the text and run it. And just by running it, see, by playing with it, you get a nuanced sense of how the machine is thinking. And that is literally the exercise for you today. The next one, jumping dog, action. Then a path through a forest. The first few pictures look okay, but the last one, this one, the fifth one, rightmost one, had me surprised because it didn't look like a path through a forest till I stared at it long enough. What is it a picture of? But is there a path through the forest? It's an aerial view of a path through a forest, which is snowed over. And a machine understands that in the blink. So you can do different things, cars, etc. But this was a term that a previous participant asked. Could we search for something really abstract? Serenity. Serenity is much harder to search for with keywords, isn't it? Now, one question. Did these images come indexed with keywords? No. They're just images you have dumped onto a machine. No hints, no keywords, no metadata. Would you agree that this conveys the emotion? That, folks, is the power and potential of language models. That is what we are going to harness to build genuine enterprise class powerful applications. In previous cohorts have within 2 to 3 weeks taken this learning, gone to their workplace and had a genuine impact. I hope you will repeat that or beat them. Many startups have come from this bootcamp. I hope you too will follow in that great tradition. Your questions. Large helps you get funding or language. Why is it so the question I'm getting is, why is it called a language model? Thank you for asking that question. See, and it would be a good point to end. What is language? Human beings, before human beings, before we were even monkeys in trees, or before reptiles and so forth, fishes had eyes. And snakes, reptiles have eyes, amphibians have eyes, mammals have eyes. Our understanding of the external world, our communication with each other, for the longest time was visual. We communicated with each other by making pictures on cave walls and by seeing things. A picture, as they say, is worth 1,000 words. Pictures, images are a language. Videos are a language. Sound is a language. For the longest time, animals communicate through sound. Their language is purely sound. Humanity communicated through sound. When I came, when I grew up in India, long, long ago, the literacy rate was between 15% and 25% in the country. 75% of the country did not know how to write, but they communicated. For thousands of years, hundreds of thousands of years, mankind has communicated through sound. Language has come to our ears and spoken through our tongue. The written form is very, very recent. But because we are all people with shirts and pants and have gone through colleges, we seem to get a little bit jaundiced view that language should always come as text. But it isn't so. Language is a medium of communication. With that definition, images are images tell a narrative, videos tell a narrative, sound tells a narrative, and so does written text tell a narrative. And so language model, it's part of its awesomeness, its majesty is that it is multimodal. It not only understands all the written languages, all the spoken languages of the world, it understands languages in multiple modalities, as sound, as text, as vision. And what you are seeing is the power of vision language understanding. So the right word for language model should be perhaps language understanding models, because their core functionality is they so exquisitely understand language in all of its variations, dialects, and modalities. That is the power we are going to harness. Any other questions, folks? Go ahead. Yeah. Ah, you remembered I used most. The question from the audience is, I said, language models are better at search for most situations compared to keyword search. And why did I say most but not all? It is so awesome. Did I capture your question correctly? Answer is sometimes people don't say enough. People have gotten so used to entering keywords, they don't realize the unnaturalness of this. So let's go back to the example bank. If you just use the word bank, a language model would go, okay, which bank? But a keyword search engine might remember statistically this Silicon Valley blokes or this particular document that you have or the documents that it is indexed are all about financial bank. So there are situations where the input is not semantically rich. Because remember, these are language understanding machines. So if what you give it is not rich enough in meaning, they will underperform. But so long as you are expressive enough, they will. In fact, there is a very interesting paradox. Have you noticed that when you enter a lot of keywords in a keyword search engine, they actually come up with, they begin to underperform. The longer the input, the worse they do. On the other hand, language models, the longer the input, the more carefully you narrate what you want, the better they are at getting you precisely what you want. So that's an interesting asymmetry. All right, folks. So I'll give you guys a 15-minute break. And how about we regroup after that? And I apologize. I
Should I
have
show
ordered
that
your lunch.
error?
Oh,
In
yeah,
the
let's do that.
meantime,
Let's do that. Yes, let's do that. It's
I
already
just
done, huh?
show.
Yes. Please.
I just did the one error. It identified it well. So
Yes. So,
so
guys, look at this. This was not pre-cooked. We just cooked it up now.
sorry. Here,
Let's see
just
how
now.
well it works.
So I deliberately created an image which had a square and a plus sign, and identify errors if any in this and fix them, then explain the concept and the corrected equation, also give a PyTorch code. So I did it right. So it said there is an incorrect update rule. There's a square term, and then it gave the corrected equation and gave the PyTorch implementation also.
How many of you are blown
Pretty.
away by this? That, again, guys, is the awesomeness of language. Guys, I'll pause here. Hey, Chandra, thanks a lot. And it's getting very late, so I'll let you go.
Yeah. I think during the break I will drop off.
Yeah. So today was about, in this lesson plan, we are going to talk about what we are going to do today. What does it mean for a machine to understand? We'll take a simple journey. this is also a hero's journey. This course is, while I'm saying it's easy to understand, it is nevertheless strenuous because we have a lot of projects, labs, quizzes that will build up your muscles. Our goal is to put you in the top few percent, 5% at least of the field. To do that in just a course of 3 months needs Herculean effort from our side and also a commensurate effort from your side. But if you do put in the effort, at whatever level you are, individual contributor or leadership, but if you bring in energy from your side, you'll get a lot out of it. Theme of the week is, what does it mean for a machine to understand language? We'll go through that. Now, when you, through this lecture, every week, when you see this document, look to this section. What must you carry forward? In other words, after all is said and done, and after we have had 5-6 hours of dense material, you may not need to remember everything. But what is the minimum required that if you carry forward with you, you know that you are making progress? So here, for today, it is articulate a working definition of understanding appropriate for machines. Are we getting a sense of that? Machines understand thoughts as points. That's their machinese. Explain why semantic similarity does not require keyword overlap. Describe how context reshapes meaning in languages. That is yet to come in the afternoon. Interpret attention as a means, as a mechanism for meaning preservation and retrieval. Distinguish surface language behavior from internal representation. So how you word your text doesn't really matter. What matters is the actual meaning of the text, because that will decide where in the embedding space you land, the point lands. So some of it we have been talking about, some of it we'll talk in the afternoon. But in the afternoon, we'll progressively dig a little bit deeper. We will do the landmark paper called Attention is All You Need. How many of you have heard the buzzword or the title of this paper? Attention is all you need. How many of you would like to understand what it means? So we'll do that today afternoon. But we'll have lunch first so that we are soothed down and it doesn't feel scary. Lecture outline. This week's labs, you will have coding labs, as I said. Chanda will be leading that. And it will be simple labs to get you warmed up and started. This lab, just to give you a perspective, those of you who have registered, by the way, I have no idea how many of you have and haven't registered or plan to register. Reach out to me during the lunch break. But all of you who have registered, you will get VPN access to the cluster. That's a 24/7 access. We request that you do not share that access with other people, please. It's an honor system. Please respect that. Once you have access to it, you'll get a VM. That VM is on the cluster. That cluster that is a GPU cluster. You will learn to submit jobs on the GPU cluster for AI training. You can get a GPU on demand. There are lots of GPUs we have, and most likely you won't feel the shortage. If you do, we'll get more GPUs. These are powerful GPUs and should keep you entertained. Get started with your labs early. You'll get a lot out of this project. As I said, one of the key things that is hard to get is this level of compute resources to learn. So use it. The second is access to the TAs. Use that access to the TAs. Essential reading. Now, every week, we'll come up with 2 reading lists, guys. One is essential reading. It is the only thing you need to go and study. And most of those things I would have covered in the class. At least one of the things, the hardest one, I would have covered in the class. The other 2 would be simpler. But these are landmark things. If you do read it, you'll make a lot of progress. Then we also create what we playfully call the Oliver Twist list of readings. You remember the story of Oliver Twist? It's a Dickens story. It's a boy in an orphanage who asks for more food. So anyway, for the voracious minds, these reading lists are optional, but each sharpens judgment rather than adding surface familiarity. So what we do here is, this field is very rich. There's a lot of literature here. And if you want to know, I'm done with the core reading, what else can I read? How can I learn more? Then go to the Oliver Twist. We don't expect you to go to Oliver Twist, but we hope that you go. You don't have to pick up everything from the Oliver Twist list. Sample into that. The first one that we mentioned here, JLMR, the illustrated transformer, started out as an article. It's a GitHub, and it has also become a book from O'Reilly. You may want to pick up that book as a adjunct to this course. Andrew Karpathy has written quite a few articles. This one in particular is very good. And it talks about RNNs, a previous architecture we'll talk about. Chris Ola is one of the tech leads at Anthropic. And his article, A Mathematical Framework for Transformer Circuits, very deep contribution. Again, not for the faint of heart. The one suggestion I could give is keep the Oliver Twist as something you will read next month. You know, when you have enough maturity on this topic. So whatever I give you as Oliver Twist list now, read it next month. But you should at least have it. And so this is how it will be. Week 1 is deliberately expansive and reflective. See, we are talking at high level. I'm trying to orient your thinking process, because we won't get a chance to do that. We'll get into deep details and implementation, and let's build this and let's build that. But this week I've kept for just reorienting ourselves and thinking correctly. So do not mistake this breadth for vagueness. This course is not vague. It's pretty, you'll realize that we are very implementation heavy. Our aim is not to rush towards implementation, but to ensure that when you do build systems, we understand why they behave the way they do. So you all have this document with you. Do read it in the break. What I would like to do now is launch forth in this concept. How long have we been trying to make machines learn a language, human language? One would imagine that that would be one of the oldest aspirations we could have. What if machines could understand us? How many of you have gone and felt the need to kick the printer when it doesn't print things the way you want it to print? Or other machinery, like you get totally annoyed with your car or something like that when it doesn't obey you. So we all want machines to understand us and follow what we ask it to do, even if we don't say it very clearly. So people have had prior efforts to do this. The language models today have become synonymous with what I call transformers. But I'd like to go a little bit before that and do an architecture that came before it. It was called recurrent neural network. I won't go too much into it, but I'll give you a flavor of what it was and why it didn't work. So the topic is a very complicated name. It is recurrent neural network. Recurrent neural network. What it has is something very interesting. It says, suppose you have a statement, the cow jumped over the moon. By the way, we won't give you labs on RNN. We'll go straight to transformer. So this is not part of this is just for understanding. The first word goes in, into this machine. So I'll call the word that goes in as XI. It goes in. The machine says, what could it mean? Okay. In its private diary, so imagine that you have only one page to write on. The machine doesn't know that more words are coming. So it will write in its machinese the whole word, use the whole page to write whatever it got, one word. So it comes up with a hidden representation, H1, You gave it the first word. Then what you do is, you say there's another word coming. You give it the second word, and the way you do that is, you pass this word, whatever is written on the page back in. And so then x2 goes in, and x2, so if you think of this as a function, you can say that this is a function of x1. The second hidden state is a function of x2 that you're giving, the next word that you're giving, which is the cow, and whatever you have written on the page before, because you're going to add to the page. In some sense, what the machine does is, it thinks about it, it sees the word the is written, the word cow is written, it erases what was there and rewrites a new representation. And it keeps doing that over and over and over again. So at any given state, ht plus 1, the next understanding that it has is some function of the token that you just gave and the hidden representation that it had up to then, what it had written up to then. So what will happen? Suppose, imagine that I give you just enough text. You have space on the page to write it pretty well. But if I keep on giving you text and start pouring a textbook onto your head, what will happen now? You will be forced to summarize and condense it. At some point, what will happen? It will start getting lossy. You will start not capturing all of it. You'll try very hard to condense it all in a finite page. Limitation is finite page. The other thing you remember that it is very, because it focuses on the word that you just gave and then the previous state, the recent words tend to have overwhelming importance. And the words way back when, in the beginning of the sentence or the beginning of the document, they begin to fade. Just like human beings, if I keep talking to you for quite some time, most likely you'll remember the end of it. And RNNs behave like that. They are somewhat like that. So they have a problem, recency problem, a compression problem, because they have to compress so much knowledge into just a page. They also have some practical engineering problems. They are not parallelizable machines. So when people, in AI community, there was an interesting phenomenon. AlexNet came in 2012. It was a big moment. And when it came, computer vision got revolutionized. The old computer vision began to get replaced by neural networks, by convolutional neural networks. In fact, some of the computer vision community, computer vision conferences, they practically sounded like funerals to the old computer vision. It was that powerful, the convolutional neural network and the deep networks. AlexNet, ResNet, VGGNet, Inception, all of this going. One advantage of those networks was they could run on GPUs. So NVIDIA, which was making video cards for graphic designers and for gamers, all of a sudden found a new market. The rest is history. So it did extraordinarily well. Why? Because you could do computer vision on their GPUs. Parallelizable computations. But the text language community was not having a good day at all, because this machine, to create the next state, it needs to have the state so far and the next token, one at a time. Tokens go in one at a time, isn't it? It wasn't parallelizable. So there was a computational bottleneck. So they were looking at the computer vision community having a fun time with GPUs, while they couldn't make what to do with the GPU. Within these constraints, a new paradigm came. And that is the importance of that paradigm. It was based on attention. So we will talk about this wonderful, wonderful concept of attention. How many of you know what attention is? Or have read some articles, papers, listened to lectures? Just show of hands. Couple of you. What is attention? Would somebody like to articulate? Not somebody who has taken my course and is repeating. Somebody new. What is attention? Just in common language. See, at this moment, as I'm talking to you, the air conditioner is humming. There are distracting sounds. People are fidgeting in their desk. There are two monitors here displaying text. There are many things competing for your attention. Nevertheless, so your visual field has many things. Your total sensory field has many inputs. There's the humming of the air conditioner. There is the TV monitors. There are the TV monitors. There is me speaking. There are people fidgeting. Right? And there's different sounds happening. And yet, of all the inputs, you are paying disproportionately large amount of emphasis to one input, which is me. Why are you paying attention? Why are you giving so much emphasis to what I am speaking? Because of the context. What is the context? Why are we here? To learn about language models. So the context determines what you are paying attention to. If a facilities manager came in and wanted to worry about the air conditioner, he would be ignoring this talk and listening to the sound. Do we get that? So context determines which of the elements of the input you will give more emphasis to. Isn't that absolutely intuitive? The definition of attention is when a teacher says, pay attention. What do we mean? Your emphasis was looking out of the window or talking to your friend. And teacher is not happy with that emphasis. You are paying attention to something, but she wants to change your context. She wants to say, what I'm teaching is more important. Therefore, pay attention to me. Excuse my spring allergies. I'll illustrate this with something real that happens to me. I go hiking in the morning. When I go hiking, because I like astronomy, I like to meet my old friends, the stars in the sky. So I start out 90 minutes or so before sunrise. At that time, I go hiking on a trail next to a creek, which is somewhat forested. So in the beginning, I'm seeing my favorite stars. These days is the winter star, but you can see, you look up, you see a Big Dipper putting a big question mark in the sky. Then you see the Cassiopeia with a big W, again for Y. I always like to look at those because it reminds me that the day should be lived asking the question, why? But anyway, as you make progress, lost in the beauty of the star, gradually the first light of dawn comes. You see a mist over the river, blanket of mist, which slowly begins to lift. You see the first light over the hills. It's all beautiful. Your mind is lost now, and the stars are fading. Your attention has moved to a different thing. All of a sudden, you hear growl of a predator. That's why the cover of this is the scene, by the way. That's on your lesson plan. Do you see that mountain lion? You hear a growl. You were looking up there in the distance. Now, where are you looking? Where is it? Where is it? Isn't it? Are the stars still there? They may be, but they have disappeared as far as you are concerned, isn't it? What about that beautiful mist or the first light of dawn? Everything is forgotten, and your eyes are on the mountain lion. That is attention. The context initially was, appreciation of beauty that is there. That's the unfolding of the dawn. So you're lost in that. Your attention is at stars, stars on the first light. But the moment you hear a growl, what is your context now? You don't want to become breakfast. Yeah? You don't want to be the DoorDash delivery coming on your own to the mountain lion. It's survival. So that is attention. If you understand that, trust me, we will quickly translate that into mathematics. That is easy. Now, think machines. How do machines think? We just thought about it. They think as vectors. So let us say the context is this. The context is this. And you have points A, B, let's put C somewhere, C, D. Oh, maybe I should use a different color. Which of the contexts, which of the, sorry, in pieces of the input, A, B, C, D, looks most relevant? A. It is closest to the context. In a more intuitive way, suppose you're hearing a conversation in the bar. Your context is some technical topic, and you hear one person discussing that. Your ears naturally tune to that person. Is closest to the context. So, because these are vectors, would it be reasonable to say that a good measure of how much weightage you give to that vector, to that input, would be a dot product between dot product measures alignment, isn't it? 2, if A is close to context, it would have a much larger dot product as opposed to B. So score A will be greater than score B, will be greater than or more or less the same as score C is greater than score D. Go ahead. Oh, we are not talking of LLMs yet. Just the foundational concept of attention. Now what we can do, suppose I do this. I say, what should I be looking at? I don't want to ignore B, C, and D. A is closer, but B and C also deserve some respect. So what I could do is, I could do this. I could say score A times the A vector plus score B times the B vector plus score C times the C vector plus score D times the D vector. What will it more or less point towards? It will more or less be somewhere, if I were to represent it, it would be more or less, let me use a different color. It would be more or less the same vector, give or take. This final vector, oh, I should not call it. I will call it ATT vector. The ATT vector captures our intuition of attention in this given context. Are we together? And that mathematically is exactly the definition of attention. all we can do is scale it up. If you want, scale it up with the sigma, that is that way they all add up to 1. All the scores are dividing as unit pi, but that is a technicality. This is attention. Now, let's take an example, because suppose you have handwritten 4 cards, 1, 7, 5, 6. And you want to feed it to a machine, some form of a neural network, and you ask it, which is the biggest number? You did not give it number. These are handwritten digits. This is the famous MNIST data set. 4 cards with hand scribbles, handwriting of digits. It's a hard problem. We are not saying, tell me what is written on 1 card. We are instead saying, I'm giving you 4 cards, tell me which is the biggest. You realize that not only you have to infer what is written on each card, but then you need to contextualize it, compare it to others. It needs to find its full meaning. One looks at others and says, I'm not the biggest. 5 looks around and says, I'm bigger than 1, but not yet. Likewise for 6. 7 looks around and says, oh, I'm the biggest. So you cannot answer this question till each of the cards have observed the context, which is all the 4 cards. People have tried this experiment. If you build a neural network with just feed-forward network or convolutional networks, the older technologies that used to exist, then, and you look at the accuracy of the model, how well is it able to tell the greatest, when you keep showing it 4 random cards from the MNIST dataset, 4 random images for the MNIST dataset, what they found is you get a certain accuracy, which is with a good feed-forward network, you'll get somewhere in the 90%. But the moment you bring in attention into the game, an attention network, in other words, something that encodes this formula into PyTorch, the moment you do that, this takes a huge, I should make it upwards. This takes a huge jump from 90 to, I forget the exact number, but it was closer to 97%. That is a huge jump. If you think in terms of error reduction, you reduce the error by 1/3, down to 1/3 of itself. That shows the power of attention. So people began to realize that attention is a very powerful concept. So for a couple of years, this became the tradition. Whatever neural architecture you were creating to solve your problem, people would think, add attention to it. It's an advanced thing. If you add attention to it, it would do better. And sure it was. It did better. It made convolutional neural networks do better for image processing. It made recurrent neural networks do better if you threw attention blocks into the mix. So people treated it as an advanced additive. It's almost like vitamins, or I call it pixie dust. Attention acted as pixie dust. You would sprinkle it on whatever neural architecture you had, and all of a sudden, it did better at the task at hand. And that was the prevailing thing, that very useful. No one realized its core importance. Then came a project at Google. Google was in the business of web, Google search engine. Text exists in many, many languages. Sometimes you may ask a question in English, the answer might exist in Spanish. And they could easily translate that into English and answer your question or find you a document or something like that. Translation was core requirement, summarizing docs, many of these natural language tasks was part of their domain. So they said we need a good language model. At that time, what were the good language models? Recurrent neural networks. It turns out that you could also use CNN, convolutional neural networks, to get your job done. But they were not as effective. Recurrents were the king of the hill. So before 2017, RNN was the go-to. That was the orthodoxy for NLP, natural language processing tasks. And CNN were for computer vision. But you could do some NLP occasionally with CNN also. So they said, okay, we need to really solve this problem. A bunch of engineers got together and asked, what do we know? We know that RNNs work. We know that sometimes CNNs also work. And we have this newfangled tool, advanced tool, attention. We throw that into the mix. We'll have the Uber model, the ultimate model. So they call that model what could C stand for? CNN. A, attention. R for RNN. Go for Google. And net for neural networks. So they built it and it worked quite well. Now they asked this question. It's called ablation. How much did each of these components contribute to making this model perform? Because if you know that, let's say RNN is the king of the hill, you can make that area of the network bigger. You can invest more and more into it, do more research into it, do many fancy things into it. So they started doing this study that between these three players, CNN, attention, and RNN, what is their differential contribution? So they first removed, let's say, and here I'm making the narrative up a little bit. They got rid of the C. And they realized that the model performs more or less just as good. Were they surprised? Not particularly, because RNNs, CNNs were not that big deal in natural language processing. So they said, okay, let's leave it alone. They went to attention, let's say, and they took it out and the performance came down. So they said, oh, of course, we know that attention is a pixie dust. You add it, things work. So far, so good. Then they go to RNN and they say, let's take this out. That was breaking away from the orthodoxy. Nobody would think of throwing RNN out. So when they took the RNN out, they expected a catastrophe. What they found instead is that the model was just as good. And what? We have all been conditioned into the belief that natural language processing should be done with RNN. But what they found is you could take RNN out so long as you kept attention there. And so they realized that this is what they need to focus on. They went heavy into it. If one attention network is good, one block is good, let's have many blocks. Let's put them in parallel, let's put them in series, right? Create a whole pancake out of it. And that's what they did. And what came out of that is a new neural architecture called the transformer. And it is in the paper called Attention is All You Need. Now, this phrase has the history that I just told you. Does it make sense why it has that title? Attention is all you need to do natural language processing. In fact, today, we don't call it so much natural language processing. We call it language understanding. Recall that since morning, I did not use the word processing at all. I kept on emphasizing the word language understanding. So the new word is NLU, natural language understanding. But then when we extend it to vision, it becomes vision language understanding. And then you extend it to audio, then it becomes audio language understanding. So at the end of it, why not just say language models understand languages? So that is the journey that we are going to embark on in this paper. So now we are going to dive a little bit deeper and go into a paper. So for that, to give you this paper, attention is all you need, I will take a text. Let me cook up a sentence. See, let's say this. Now, look at the word bank. Bank is an interesting word. We talked about the fact that it can have many meanings. From that, we concluded that the meaning is disambiguated by the context. And we just learned how context comes in useful through the attention mechanism. So the word bank can go pay attention to all the other words to disambiguate itself, to understand its true meaning. So far with me, guys? Now, how can it do that? Look at this word. Harry went uh, went to went to is the word there in the sentence, but it is there. Semantically, meaning wise, it's there. Even though the word bank doesn't exist in the sentence, it is nevertheless hiding in there. Where is it hiding? Yes, it is hiding in this word, Wells Fargo, which word itself is not an English word. But the context paints it to be bank. And therein is an interesting lesson for us. A word and the context. the full meaning of the word may be in the word itself, or it may be in the context, or it may be somewhere in between. You would need some part of the word and some part of the context to get it. The word plus some context. Is that a good takeaway lesson? Take that lesson away. Sometimes, for example, if I say the word turnip, probably much of the meaning of turnip is in the word turnip, but not for the word bank. And nothing of the meaning is there in the phrase Wells Fargo. That's the lesson to take away. Once we have taken that away, what we need is to think about a dictionary now. In a dictionary, what do we have? We have words and their meanings. So imagine that you encounter a word, but you don't find it in the dictionary. But what is your instinct then? If you find the word in the dictionary, you read the meaning. Life is easy. Let's take a real word, but let me try to pick a word that may be unfamiliar. Apogee. How many of you know what apogee means? What does it mean? Excellent. Highest point in an orbit. But if you don't know, you would look up the dictionary and you would go, aha, now I know. The meaning has revealed itself by looking in the dictionary. On the other hand, I give you a word, let's say apogees. Or take another word, horses. Or something like that. It might not have an exact match to one of the words. What do you tend to do then? You encounter the word horse. And your instinct is? That seems to be your best hit. Let's go to that word. It may be the plural. I'm looking at the plural of this word. So you look at nearest match and pick the meaning of that. But suppose you encounter a word and there are two words or three words which are sort of in the neighborhood of that word. What would you do then? You would pick up the meaning of the word that is closest more, the word that is a little bit less matching. You would look at that meaning also, and you would somehow try to interpolate the meaning from these meanings, giving greater emphasis, greater score to the word that has a closer match. Would you do that in the dictionary? That is the idea. Now think about it this way. We have dictionaries of words, but machines speak machinese. What are their dictionaries written in? So imagine Oxford Learner's Dictionary of Machines. What are the entries there? Oh, points, vectors. Oh boy, their machines they also have keys and values, but the keys will be vectors and their values are also vectors. And when you have a word, a query, you go to the dictionary to look up that word, but machine has converted the text itself into a vector. So it is querying also with a vector. It is taking a query vector, looking up its dictionary and say, which key is it closest to? So query is the context, isn't it, for the lookup. In the search for meaning, query is the context. You want to elucidate the value of query better, of that word horse better, but horse came as a vector, as a point, and you're looking at neighboring points to that. You look for those key vectors which are closest to this. And what would you do? You would do something like this. Let's say that the query vector is there. You would compare it to every key, ki, and you would do the score. You'd say how relevant this particular entry is in the dictionary. Would you do that? Take a dot product, and then let me abbreviate it to just SI. And then you would say how much, to get the full meaning, I would do something like attention is somehow made up of this score I times the value I. Whatever meaning I see there, let me take more meaning from those keys which are near. Are we getting the intuition? We would do this. Now, the score that I wrote here, there is only one thing. These scores are not normalized. They don't add up to 1. And dot products can also be negative. For example, look at this. If these are vectors, do you notice that D points in the other direction? It can lead to negative scores. So it's not, if you want to divide your emphasis, you don't want to give negative emphasis. You want to stay positive. Parts 0 to 1 and all the parts adding to 1. So it's like dividing a pizza. There's no way you can give negative pizza to the guy you don't like. So you need to make it this. So what you do is you add a function here. Let me call this func f. And the easiest way of taking numbers and making them, 2 parts we need to do. Suppose we have numbers. Take any number, -3, 1, 5, 7, -8. How do I make them all positive? There's a simple trick, exponentiate it. That would make it positive. E to the, if E is hard, just think 10 to the power 5. These are positive. What is 10 to the power -3? 1 over 1000. Is that positive? It's also positive. So now we have positivized the numbers. But we want them to add up to 1. How do we make sure that they add up to 1? What we do is, we take sigma is equal to, add up all of these. And then every one of them divided by sigma. Would that do the trick? Not only would make all the parts, emphasis scores, attention scores positive, but they would make all the attention scores add up to 1. And now you can say that, you know what, the real meaning of the word say that again. Sigma would be equal to E1 plus all of these things added together. Right? So now I score is therefore e to the whatever value it was, the individual value ki divided by sum over j of all of these numbers. See, it looked rather, oh sorry, by the way, dot product, not ki, a ki q dot product, kj dot product. So now we have a function that will make them all these dot products positive and add up to 1. Such a function is called the softmax function. Folks, I hope this was not hard math. All we did is positivized it and then scaled it with the total. And we just discovered something lovely. It has a big name, softmax, for historic reasons. But it's our friend. And then we say that the real meaning of this query vector, because it's went in search for its meaning, is this, sum of this. In this vector is the query vector itself. Like if this word is the horse, you would realize that somewhere there would be the key of the horse itself. And query of the horse itself will also come in somewhere here. So it will pick up its own meaning, give some emphasis to it, and give emphasis to the meaning of other words that are similar to it. And then it will discover its full meaning. So attention, in some sense, is, people often call it the contextualized vector of the query vector. What went in as horse, as embedding vector, now has become a contextualized vector with respect to this text. Therefore, the takeaway message is, each word, if it goes and searches for its meaning throughout the text, they will all get enriched. They will all soak in and swell up with their meaning, like a sponge onto which you have poured water. The water being its full meaning. It will soak up and swell. And what has happened now, inside went in a text with tokens that where meanings were not so clear. Out comes a bunch of vectors now for the tokens that are swelled up in meaning. That discovery and the fact that attention, this equation that I just wrote, is the great equation that this paper, Attention is All You Need, discovered. They wrote this equation as, and you'll see the similarity. So first let me write it piece by piece, and then we'll write it as score I VI. This is what we concluded. How much emphasis to give to each of the meanings. And that can be written as I as softmax K I Q dot product times VI, because that's a score. In the score, there is also, for reasons that are computational, and this for today not relevant, there is also a scaling factor called square root of D. D is the dimensionality of the vector space. We'll just leave it there. It's there. So this is the attention for the query vector. And if you want to write it in full-blown matrix notation, it takes you to the equation that is there in the research paper, which looks rather cryptic, but it is like K Q transpose over square root of D times V. This equation is perhaps the most quoted equation in our field at this moment in generated AI. And this paper is the most quoted paper, research paper. So I've taken you on a journey to understand this. Who would like to recap and summarize what we learned? What is the takeaway? One of you, please speak up. It's all right to be wrong. We'll go through a few iterations. Attention is all you need, is certainly, but what is attention? Why do we do that? So this now becomes the self-attention equation. For a sentence or a text that has gone in, each word is now swelled up with its meaning. And the whole text is now much more contextualized. We call this the equation, the self-attention equation in the research paper. It's the only equation in the research paper. But it changed the world. What do you call this? One of you please explain to me, how would you paraphrase it in your own words? What have you understood? Try it. The meaning, value. Yeah. So look at this equation, guys. This is much more intuitive. what I wrote, in the version that I wrote. Or even better, look at it the first way, the way I wrote it in the first form, this form. Interpret it for me. What is it saying? Imagine a word like bank, which is the query. What has it done? Go ahead, Saurabh. Yeah. 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 Exactly. In context to the query, because similar to the query word, right? Looking up in the dictionary, that's all you're doing. And it's a dictionary interpretation, or it is sort of that's all there is to it in the beginning. I will later revise this interpretation to a much more nuanced interpretation. This equation, if you understand it the way I have explained it, is good for the first day. By the way, when you ask people, and I do ask in interviews, explain this equation to me, everybody will parrot out this equation. But you ask them, what is the intuition behind it? People will be like, this is one interpretation of it, simplified, but there is actually a deeper interpretation. But let's keep that for another day. Why this equation has changed the world? Why did it turn out to be so deeply fundamental? Almost like the atomic unit of intelligence. There is a deeper reason to it. And we'll encounter that a little bit later. But your lunch is here. So today, let us have our lunch and then we'll make progress. I'll pause the recording. Any questions, guys? None of you have, but before you go for lunch, earn it. One of you, please say it in your own words. Yeah. No, you don't. So what happens is, and that is a perfect example of a word, a token, that's not there in your vocabulary. So what does it do? It is empty of meaning. So it has to soak in its meaning from the context completely. Yeah, there is a representation. It will have a representation. Yes, exactly. Exactly. Yeah. See, let's think through what the attention will be. Yeah. How much more attention should you give? Would you agree that this one will get plus, plus, plus? This will get probably plus. Other things hardly matter. So you can literally see the differential weightage you would, or scores you would give to the words to find the meaning, right? But to other ones, there'll be like little lines. It will go and inspect every word, but not give too much attention to maybe a little bit to this, maybe two to this. But deposit and paycheck will get overwhelming attention from the word Wells Fargo. And thus, meaning is found or inferred. Oh, no. It would interpret it as some destination. No. Hallucination is an entirely different cause, but we'll learn about that. So today, let's, we are taking baby steps. We are beginning to build up our worldview, guys. Then we would infer that it's just a location. No, no. If the text continues, yes. So right after this, there is another sentence, let us say. Sally went to Wells Fargo. Now, what is Wells Fargo? The whole text is there. Every word is paying attention to, this word is also paying attention to deposited and so forth. And it would inferentially come to know that, oh, Sally also went to Wells, to the bank. So these machines, this attention, self-attention mechanism is extraordinarily powerful because it contextualizes. To just joke about it, you can always take meaning or completely destroy the meaning without context. Let's look at the opposite. Journalists do it. Like biased journalists, what would they do? You say anything, they will take snippets out of what you said and quote it out of context to mean whatever they want to mean, and then now they can attack you. It happens all the time. Right? Our politicians know that very well, and so they keep reminding, but you have quoted me out of context, haven't you? Context matters. Context clarifies meanings. That is a takeaway. And attention is a mechanism of enforcing that. With that, let's take our lunch break, guys. And those of you who would like to register, what we just talked about, or the intuition that I gave you, is this famous paper. Every of these researchers here have gone on to become famous for their work. Papers are written in a very technical language, but I'm hoping that now that I read the abstract, it will make sense. The abstract of this paper says the dominant sequence transduction models are based on complex recurrent or convolutional neural nets that include an encoder and decoder. Wow, lot packed into it. Right? Do you remember we talked about that, guys? That sequence-to-sequence model. A sequence-to-sequence model has a encoder and a decoder. They used to be implemented using RNN or CNN. We talked about this history. So that's what is meant by this sentence. The dominant signal sequence transduction model. Transduction model means what goes in is different from what comes out is different from what goes in. Otherwise, it will be a conduction, it's a transduction. It's a signal processing language. Don't read too much into it. Are based on complex recurrent or convolutional neural nets that include an encoder and decoder. The best performing models also connect the encoder and decoder through an attention mechanism. Did we talk of attention being the pixie dust? They add that also. So they are saying, so this is the history of the field. Next sentence says, we propose a new simple architecture, the transformer, based solely on attention mechanism, dispensing with recurrence and convolution entirely. Is that what we were talking about the last hour? Experiments on 2 machine translation tasks show these models to be superior in quality while being parallelizable and requiring significantly less time to train. So here are the key points. When this paper came out, it was sort of by experimentation. Oh, we don't need RNN. Oh, we don't need CNN. And we hit upon attention. And they did an amazing job. Nevertheless, look at the emphasis in the paper historically. This is now ancient history, right? It came out in 2017 summer. That feels like ancient history. And you can see the changing emphasis. Researchers didn't quite grasp what a big thing they had stumbled upon, how fundamental it was. So they are focusing on the fact that it is giving you better performance than previous models, which is important to be taken seriously. But more importantly, they are focusing on a big limitation of RNN, which was that they could not be parallelized. In the case of the whole text going in, every word searching for its meaning, they could do that in parallel. Each word becomes a query, context, searches for its full meaning by observing the other words, this entire thing can be done in parallel. That was considered the big breakthrough because now you can have high throughput. They go on to say our model achieves 28.4 blue on the, and basically it achieves very good benchmark scores. So all research papers are written in this format. Introduction, in which you give the background, you make a case for what you did. Method, what is it that you did? Results, okay, that results in our field is mostly like you beat the state of the art and you achieve new scores on the benchmark. Conclusion, then you put your final thoughts. And then the final thoughts is here. We show that the transformer generalizes well to other tasks by applying it successfully to English constituency parsing, both with large and limited training data. So they say that, okay, it's a, and herein is the concept of a foundational model. A foundational model is a model that you train and you can use it for many purposes. It's generalizable or usable for many downstream purposes. That's what they're doing. Now, there's a lot of conversation in this equation, in this thing. But first, I would like you to pay attention to, does this look like an old familiar friend now? It does. And see, I built the encoder and decoder horizontally. Here is written vertically. Input goes in. The left-hand column is the encoder column. Encoder's hidden states go into the decoder. Do you see the decoder column here? Is the decoder column. And then the output comes in. This is the, today we call it the classic transformer architecture with both the encoder and decoder present. It turns out that for many tasks, you only care about the language understanding part, not the decoding or some output part. So those are called encoder-only architectures. There are tasks which use only the decoder part, though one would argue that encoding still takes place in the early layers, and those are called decoder only. The two big families that came out of this architecture was the BERT family, which was encoder only, and then the GPT family, which was decoder only. And a lot of these chatbots that you see, they are decoder only family chatbots. And something to mention that this one, they represent the math using these two things. What do? We do K and Q. Do we do a dot product between them? In the way we talked about it, if you look at it here. I represented it in a bit more intuitive way. This is the dot product between the, hang on. A dot product between the query and the key to get the score, guys. That is what is being talked here. Dot product, scale it by square root of D, and then softmax it. Why do we softmax it? Remind me. Positivize it and scale it so that they all add up to 0. All the scales add up to 0. And then finally, those scores are multiplied by the actual value, which we saw. Now, there is a concept of multi-head attention. I will introduce that now. This paper we will do in many iterations over the course of this bootcamp. Today, I'm giving you the highlights, but there is a lot of subtlety still to be discussed, which we will keep for the next time. But I will talk about multi-head. See, when people realize that one attention head is good, what do you want to do with that? More is better. Right. So let's go absolutely crazy with it. So they put attention, then they layered attention on top of it, deep layers of attention. Okay, that is good. It's looking better and better. How else can we have more attention heads? Let's add them in parallel. In each layer, let's not have one attention head, let's have many attention head. Why would you do that? If the same input is going, why would you put multiple attention heads? That is something worth discussing. See, neural networks, and those of you who are in my Foundations of AI course know this. neural networks, under the pressure of training, backpropagation, gradient descent, the learning process, all the blocks in the neural network, they start playing a cooperative game. They ask each other, how is it that we cooperate so that we learn the most? So just as in a team, if a task is given, one will say, I'll take care of the UI, I will focus on the database, I'll focus on the APIs and middle tier, I'll focus on the AI model. Do we do that? I'll focus on the QA. People divide responsibilities and emphasis. In the same way, if the same input is going and a layer as a team is supposed to produce something worthwhile for the next layer, what happens is these elements, they start playing a cooperative game. So how can they play a cooperative game? One focuses on, let's say, more on the grammar. One focuses a little bit more on the um, tone and nuances of the text. One focuses on something else. Because then, if they all focus on different aspects of the text, it seems natural that their understanding, their semantic extraction, the semantic sense that they extract from the tokens will be superior, wouldn't it? And that's the argument for putting within the same layer multiple heads and taking the joint concatenated result as the understanding coming from this layer, going to the next layer, to the next layer, to the next layer. Did I lose you all? How many of you feel you sort of got it? Okay, I'll say it again. See, two friends go and attend classes. And the subjects are very hard in college. Or maybe you come to my class and two friends are finding it very hard. So one friend decides, hey, I'll focus on the stories and metaphors so we don't miss it. Another one says, okay, I'll take down those equations that he writes. And a third one says, okay, I will take down all those pictures, geometry pictures he keeps making, points on a surface. Then later on, we'll put it all together and make some head and tail out of it. Would that look like a cooperative game? And would that be advantageous? Because each person has certain cognitive ability. They don't trust that any one of them will get everything on their own. So they all differentiate responsibilities. That is exactly what happens in a neural network when you put blocks in parallel. They act like friends who says, hey, you focus here and I'll focus here. That is the concept of the multi-head attention. Many of them together. So you see that they are stacked together. That's all it is. Intuitively, that is all there is to it. It's not that I'm giving an oversimplified picture. The core idea of putting many at the same time is that. And that is it. After that, you look at the results, so they concatenate this. And then, when you look at the results were spectacular. Right at them. And these transformers began to beat the state of the art on the very first go. Look at the last line. Look here. Oh, where is my... Look at this and compare it. Any one of them, let's compare it to this column. Any one of these columns that you look at, would you agree that both of these columns, it's doing extraordinarily well? It's beating the state of the art. And that was it. A model, the value of this paper was, great papers open the door that can lead to a lot of new research. This paper opened a vast doorway, perhaps much more than the researchers realized at that time. Today, all the magic that you are seeing in the last 5-6 years in AI, a large part of it has come from this breakthrough. And you're literally seeing how an effective new paradigm for an effective language understanding model is born. Questions? Yes. Yeah, sort of. What you're doing is you're saying, first, what we'll do is all the words are in some sense dehydrated. Let's soak them in to the context to swell them up to their full, hydrate them to their full meaning. And then let's continue forward. That's all it says. There is no. So when you build this architecture, the big realization was you don't need those things at all. People had a belief, it was the orthodoxy, that you cannot do natural language processing without those two elements. Attention was supposed to be the spice. It turns out it is the main dish. So think of rasam. Spice is all you have. Right? Yeah.
Greatest, greatest thing there right now. So how similar is it with whatever it was knowledge, or is it like completely different now?
Say that again.
Greatest and the greatest.
Oh, fundamental architecture has remained the same, but changes have happened. A lot of research is centered around optimizing this, scaling it up. There's some lot of details I have skipped for the first time, but position embedding has improved. Then DeepSeek has brought three major innovations. One of them is the latent attention head. One of them is the residual channel innovation. They transform that. One of them that is just very recent is adding memory to transformer. So converting it from a pure compute engine to an engine with memory. And that has been a game changer. That just happened on January 12th. And the fact that they did major engineering to the innovation to the residual channel. Does the word residual channel ring a bell with any of you? Okay, so this is again a neural architecture. I'll explain it to you in a moment. That has gone through a revolution. And just the attention, the keys and values, they have figured out a way to compress it, which has speeded up the whole inference. One of the big problems today is we have ginormous models, and the computes happening per request is huge. So through compression, they have scaled it down almost by a factor of 37 or something like that. It was amazing. So those are the innovations. Innovations are happening practically every week in this space. But nevertheless, the core backbone has remained this thing. I showed you not the details that would disappear. Notice that many aspects of the paper I didn't go over the details of. But what did I fixate on? The attention equation. That is the invariant. Through all these years of research, nobody has been able to shake that out. That stands. And one of the deeper questions is, so much of attention and the transformer has been re-engineered. And people have tried and tried to replace the attention equation. There is a problem with the attention equation. It's quadratic, remember? Every word has a query which goes and inspects the key of every other word. If the number of tokens is n, there's an order n square compute, the dot products. So that is computational nightmare. So people thought, yeah, with time we'll linearize it. We'll make it simpler. It's just like normal software engineering. Nobody is happy with bubble sort. So what do you come up with? Quick sort, merge sort, whatnot. Right? So they thought they'll solve it, but it hasn't been solved. Almost, in fact, every effort in the general to linearize attention has failed. And you can do it for specific domains and partially, like just for vision and partially, but not in the generality, and certainly not for text, etc. You always take a performance hit, quality hit. And there's a deeper reason, I believe, why that equation that I taught you cannot be shaken up. It is the bedrock. Now, what I will do is related to search. We did search today, isn't it? Would you like to cross over the dots from theory to actual practicality? How much time do we have? Oh, it's 3. We have only 2 hours left. I trust you guys are willing to be here till 8 p.m.
Right.
So there is another research paper, BERT, bidirectional encoder. So instead of going into the technicalities of it, do you realize that understanding it intuitively, then going and looking at the paper is a lot easier than starting with the paper and making head and tail of those very big words? So we'll do intuition first. Let's do that. So we close the chapter on attention. Can I assume that we have learned attention now? Understood the core intuition. You should have, guys. Now, see, you may suspect that I've given you a baby picture, that there is a lot more to it. It's not like that. What I explained to you as the meaning of attention is the complete picture of attention, equation and all. It is the totality of it. So if you have followed whatever I have explained today, you have understood attention, which is the foundational building block of modern AI, modern language models.
And so if you have a big query, then you were saying that it needs to do the quadratic check. And if you're actually giving a big book to actually summarize, so then, I mean, is it like very difficult?
Very expensive. So the question is that, hey, if you give a whole book, the quadratic cost will blow up. It does blow up. And those people who give you frontier models and charge you for the tokens, they love it. No, I'm kidding. But yes, computationally it's brutal. Don't do that. Don't do that. There are smarter ways to deal, and that's exactly what you learn in this course. So now we close the topic on attention and ask another question. A text becomes a vector. So a text T becomes a embedding vector. Ti becomes an updot. Now you say, well, vector, how did it become a vector? I will give you 2 answers to it. See, we said that we are going to project this point on the globe. So let's make it a little bit nuanced. Our globe, the surface of it is what dimensional? Surface, 2-dimensional. Most of us can't fly off, so 2D. So 2D. So a 3-dimensional sphere, the surface is a 2-dimension. So a 4-dimensional sphere, the surface will be 3-dimensional. Now a 1,000-dimensional sphere will have a surface that is 999 dimensions. That is it. So, no, but how do you visualize 999 dimensions? Easy peasy, right? I'll tell you a trick. I came to graduate school in US, and I found in the department people were glibly talking. There were superstring theorists, and they were glibly talking. As you can see in 11 dimensions, this happens. And I kept looking there, and I couldn't see a thing. So I thought maybe I need to shift to another research group, which is talking something that I can understand. So then there were gravity people, general relativity people. Then they were saying, and this, and therefore, as you see in 4 dimensions, I felt really dumb. I couldn't even visualize 4 dimensions or see anything in 4 dimensions. Can you? So then a friend told me at Trek, he said, actually, you visualize it on a page, but when you speak loudly, you say, as you can see it in 1,000 dimensions. Most of the time it works. That's how you extend your intuition. For today, at least, that will do. But later on, we'll know that higher dimensions are weird. There's something very odd going on there that actually we are beginning to understand only in the last few years. But for now, we'll just imagine that if you take a text, it becomes a point on the globe. The surface of the globe just happens to be 1,000 dimension or 100 dimension or whatever high dimension, and not just 2 dimension. So now the question is, why not 2 dimension? Why can't we take all the text and tell the machine, hey, don't go about putting points on some very high dimensional surface. I wouldn't be able to see it. Just stick to 2 dimensions. Why would I not do that? So let me give you, let's see if the following intuition works. Let's talk about cows and ducks. Cows are big, heavy animals. Ducks are small, feathery little things. So look at the word cow or the word duck. And suppose, imagine that you are the machine and you need to think of these words as a point. So how would you do that? Let's take the weight and the size. What you would say is that these purple little things, lightweight and small in are ducks. And this big heavy things are all sorts of cows. Would make sense? But now you have a problem. There comes, let's say, a sofa. Sofas are big and heavy, but you would agree that they are not cows. You would rather sit on a sofa but wouldn't want to try sitting on a cow. So we need one more axis, animal or thing. Because the word cow has built in not just a size, a notion, a characteristic of size and a characteristic of weight, but also that it's an animal. So you add one more axis. But then comes a horse and says, hey, what about me? Now you need to distinguish the cow from the horse. You need to add a few more axes to those. What are you doing? To capture the full meaning of the word cow, the full meaning of the word horse, full meaning of the word duck, these words are packed with so much in them, so many characteristics in them. These words culturally that we inherit through thousands of years of language are sort of condensed representation of something that if you were asked to describe to an alien, it would take you half an hour to do so. So in other words, they have many dimensionality to them, many characteristics to them that you need to talk about and quantify to give full color to the meaning, to the word cow, to fully explain the meaning of the word cow. Are we together? What we are saying is you need to have a rich number of dimensions, not just 2. Lesson? We need a sufficiently high dimensional space to represent words. But now comes a problem though. We can't just go on say, let's take a million dimensional word. Just in case we miss some nuance, there is still a few extra dimensions lying around. It's like people saying, we just got married, but God knows how many kids we'll have. So let's go get the biggest SUV. It's not like that. You can't go on getting bigger and bigger and bigger dimensional spaces because they come with problems. They suffer from a very a dreaded curse called the curse of dimensionality. Which is far more dreaded than the most dreaded curse of Harry Potter. What is this curse? And this is where we come to geometry, the last thing I want to teach you guys today. I said that all of these things ultimately are very simple geometric ideas. So let's get to that slowly. See, we live in the Bay Area. You want to talk to your neighbor. Quite often, all you have to do is stretch your hand from the window, knock at the neighbor's window, and then you can talk. Or just step out of your door and knock at your neighbor's door. Is that a common experience? You don't want to knock at your neighbor's door? He'll point. Okay. But neighbors are close by, whether friendly or not. But if you go to Wyoming or Alaska, to go to a neighbor means dressing up properly, getting into your pickup truck, driving for about an hour, and then you are at your friend's house, a neighbor's house for a visit. You know, it stretches the definition of a neighbor, doesn't it? Technically, they are still the nearest people to you. Nevertheless, it gives a completely different meaning to the word neighbor. The difference between low dimensions, 2 and 3 dimensions, and let's say 1,000-dimensional space or 100-dimensional space is exactly that. 2, 3-dimensional space is like Bay Area. Space is at a premium. We barely have elbow room. But high-dimensional spaces has just too much room in it, too much space in there. They behave like Wyoming, where neighbors are all far apart. Why does that happen? Let's see this. Let us say that you have big marbles, stones. Where's my jar of stones? Okay. Imagine that you have some stones. You have 100 stones. And you put the 100 stones in a line. You can randomly throw them anywhere on the line. So they are here. Let's make it unit distance. You throw those little stones here. Would they be relatively crowded next to each other? Now what you do is you make it a square, unit square, and let these stones have the luxury of being randomly spread out in the square. Do they have more elbow room now? There is just more room. They're spread out. They go here, 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 here. Now, do one thing. Let's make it a cube. They're spread out even more. The neighbors are getting a little bit further apart in general. Now, as is so easy to visualize, go to the next higher dimension. Can you visualize it? Okay, I'm kidding. But you can imagine what is happening. As you add more and more dimension, every dimension gives you extra space to wander out. And so, a random distribution of points, each point will be far apart from its neighbors. Do you get that geometric intuition? That is the curse of dimensionality. In very simple, intuitive terms, that is the curse of dimensionality. The curse is neighborhood ceases to have much meaning. So you practically have to get into a spaceship and cross over the intergalactic space to meet the other friend, the other neighbor. It's in astronomy, astronomers are very used to saying, pointing out, they say, look at that, it's so close. And really, there's astronomical distances between them, light years between them. So it's like that. Yes. Oh, hold that thought in your mind. Your question is there a use case where more dimensions are better? Hold that thought in your mind. We'll come to it. Now, I'm going to give you the same intuition in a slightly different way, just to reinforce the point. Can I do that? Imagine a circle, and you randomly sprinkle points in it. And you are sitting in the center of the circle. I ask you, how far do you need to go in every direction? Like, how much do you need to? Let's say that the radius of the circle is 1. What is this little radius r that you need to do to meet half your friends, half the points? How far do you need to go in terms of area covered? You would say, well, half is half. I will have to go half as far. But it isn't like that. Let's see. What is the area of the little circle? Pi r squared. This has to be a half of the whole thing. The whole thing is pi capital R squared is equal to 1. So it is, now what do you get? This cancels out. You get R squared is a half. Can you guess what R is? How much is that? 0.7, give or take. That itself is a surprise. You have to go 70% of the distance to meet half your friend, which means the other half of the friends are far away. Even in 2 dimension, I'll give you a thought experiment. Randomly think of not local, not Bay Area neighbors. And you will observe that even in 2 dimensions, a surprisingly large number of them are either on a state boundary or next to the sea or a river, lake, water body. Do this experiment. Pick 20 friends. You would imagine that most of them will be in the interior. But you'll find that a lot of them live somewhere close to a state border or the ocean or the lake or something like that. Here you're noticing half of them already are in the outer ring. Look at this. Sorry, I wish I could change colors better. They are in this outer ring. What happens when you go to a 3 dimension? In 3 dimension, r cube is 4 by 3 pi, r cube is 4 by 3. If you want to cover half of them, pi r cube, and that is what? R cube is 1. This cancels out, 4 by 3. What are you left with? R cube is a half. And so R is, which means half the neighbors, half your friends are within 20% of the border. Right? Because you want to go the area to meet half your neighbors. Now, extrapolating from that, suppose I go 1000 dimension. Can you tell what R is? What does it mean? half your neighbors are avoiding you and sitting practically on the shell. Just think about it. Half the guys are practically sitting on the outer shell of the sphere. To you, it looks like that. That is the curse of dimensionality. Means your neighbors fly away. There's too much space there. To you, it looks as though they have run away from you. So it's a bit of a lonely existence out there in high dimensions. That is the curse of dimensionality. So now we have a issue. Yeah, go ahead. Okay, very good point. Why do we care about the distance? Ultimately, all you may care about is the ranking. Who is near and who is next nearest and third nearest. Did I capture your question well? Here's the thing. Tomorrow, I want to know what is your income. Your door is locked. I can take the average of your neighbors in the Bay Area, in your apartment complex. I would get one estimate. The other estimate is I fly away to, let's say, Nevada. And there is a guy, or maybe not too far. Let's say I go over to Central Valley or Nevada and catch hold of a guy and look at his income and say, now I have a good idea about your income. Who is likely to be more accurate? Which estimate is likely to be more accurate? When the neighbors are near, when your neighbor is so far, let's take Wyoming. If your two neighbors are so far apart, one may happen to be in a completely different situation in life or area than you. That is it. Or think of political views. If I want to know, what exactly do you think? Do I want to talk to your closest friends, or do I want to talk to your far off friend, a far off guy who knew you once? That is why not just the order or the ranking of neighbors matters, but the distances matter. Because the further away they are, the less you trust that they represent you. And for us, it matters. See, a query vector comes and lands here. For us to believe that we are getting good quality search results, you would want to find other points in the polar cap in the neighborhood of that point. Now, let's say that point is the North Pole. Intuitively, it makes sense. But if you get a point that is sitting here, you would be rather suspicious. That's why distances matter. So this is the curse of dimensionality. So bringing both of these stories together, the takeaway lesson is large dimensions are way too roomy. And if that is the case, the neighbors are too far apart. If neighbors are too far apart, can I really trust these neighbors to be representative of this, semantically related to this? That begins to go down. So then comes this paradox. Too few dimensions is not expressive enough. 2 dimensions, 3 dimensions are not expressive enough. It's bad. Very high dimensions are not good because there's way too much room there. There's not much of a neighborhood anymore. And unless you're talking of intergalactic neighborhoods. So how do we win this battle? Small is bad, large is bad. What do we do?
Just see the acceptable range of locality and then use that.
So when this curse of dimensionality hits, it turns out what comes to your rescue, the knight in shining armor, is a beautiful phenomenon which is actually the real engine that makes semantic search possible at all. It is, and It's a pity that most engineers don't know about it. I'll mention that. It is called if you really want to know what is the important phenomenon, the mathematical thing, the engine behind semantic search, RAG, all of this, right? Multimodal search, it is a very deep concept called the concentration of measures. And people realize that after some time. What it says is this. See, between very low dimension and very high dimension, there is an in-between Goldilocks region. Do we know the story of Goldilocks? Not too hot, not too cold. This. So there is a middle path, there's a middle way, Goldilocks region. It's approximately between 100 to 4,000 dimension. Occasionally you see 8K, but not more than that. And typically if you see 32K, it's because people are concatenating vectors. But this is the range, the Goldilocks region. You pick dimensionality in between them. And here is why you do that. It turns out that as you go into higher dimension, and I invite you to do this experiment. In fact, this is the only lab I want you guys to do. How many of you have brought your laptop? You have. You can do this in the break. Generate 1,000,000 vectors. 1,000,000 vectors. And then of D is equal to 2, 10, 100, 1,000. That is easy. We can do that, right? NP numpy, generate vectors. Then do one thing. Find and make them unit vectors so that the dot products are cosine theta, angle between them. Measure the cosine theta by taking any one vector as a reference vector, and every other vector. Take the dot product between that vector and every other vector. So you will end up with numbers. Cosine goes from what to what? -1 to 1. Guys, do you remember that? Yeah. Cosine goes from -1 to 1. It achieves its maximum value when the angle between two vectors is 0. They're completely aligned. It achieves -1 when it is 180. And it achieves 0 when they are perpendicular to each other. What you will notice is that this is the concentration of measures. In low dimension, most of these values will be centered around 0, but in, let's say, 10 dimension, it will be like, let's say, the histogram of these values, cosine thetas, histogram, the frequency plot, histogram of cosine theta values will be something like this. But as you keep going, by the time you reach 1,000 dimension, it will be like what does it mean? Most vectors are at what angle to this reference vector? 90 degrees, right? Because the cosine with this vector is 0. That's a very interesting phenomenon. How did that happen? You can work it out, play this game. You see it. You can easily mathematically show that this happens, but to see it is very eye-opening. What does that mean? It's generally very eye-opening, because if this is the reference vector sitting at the North Pole, I'm struggling with the tool here. And all other vectors are, they seem to be where? If they are orthogonal to this vector, then this is 90 degrees mostly. All other vectors seem to be approximately 90 degrees, orthogonal to it. So it's like you sit in the North Pole and everybody runs away from you and sits at the equator. That's how it looks to each vector. You randomly picked a vector. This actually is a blessing. This is actually a blessing. So if you look at this diagram, you see why it is called concentration of measures. The mass is getting, you see this, it is getting pinched. Very sharp peak at 0 as you go to higher dimensions. It has an interesting implication. Now look at the polar cap. Suppose I look at the polar cap, it is called, the technical word you use is spherical cap. So you say, you're only going to look at this region. You are a polar bear. You'll only travel this far. And let us say you happen to meet another point which hasn't run away from you. What can you tell about that point? It is very similar semantically. It has to be, isn't it? There is no way a random point would be near you. It is all run far away from you. So if anything that you find in your polar cap must look like a polar bear too. Are we getting the intuition? You find another creature there. Oh, hello, well met. Let's talk. You have just found a friend, a semantically similar content. What does that mean for search? It means that all that a semantic search engine has to do is this journey, two-phase journey. Phase one, take all your documents, all your thoughts, each document, TI, first convert it into a vector VI using what? Language model. Because you need to translate it from English or whatever it is to machinese. Because machines understand machinese. So now what happens? You have the surface of a globe populated by all these points. Those points will have neighborhoods. All of AI content will be forming sort of like a country, or maybe a city. It will be a metropolis, which will be in the broader field of machine learning, I mean, with the broader field of computer science and STEM field, which will be sort of the continent. On the other end of the continent, maybe somewhere else will be another continent of anthropology, another continent of medicine. Are we getting the intuition? Would it happen like that? It would happen. Or so you hope. And then, suppose user wants to ask a question. What do happy cows do? Query. This is a query text. What do we do with this? Translate it back, translate it into machinese, and we get a query vector. Now we are in the land, in the latent space, in the world of machines that it sees. And what do we see here? Let us say that the query vector landed here. We just need to look for a certain polar cap around that. We treat that point as the North Pole, and we look at the polar cap region and see, are there any polar bears? If there are a few polar bears sitting there, here, would you agree that there must be very relevant search results? Because where are the irrelevant ones? They are exiled to the equatorial plane, equatorial band. See, in search, the most important thing is to find what is relevant and to reject what is irrelevant. Hold on, please. When you want to search across 1 billion documents, what do you want to retrieve? That which is relevant. But what is it that you don't want to retrieve? That which is irrelevant. Isn't that a blessing, a complete boon to you, that because of the concentration of measures, this geometrical phenomenon gives you that sort of exactly what you need, it gives you. That is the key insight that makes semantic search possible, AI search possible. That is the key thing that makes RAG and everything, all of these wonderful things that we talk about, multimodal search, everything possible. So there is a takeaway lesson here. Takeaway lesson is, you want to go to high enough dimension so that you can benefit from the concentration of measures. Concentration of measures is not showing up in low dimension. Low dimension anyway is not expressive enough. You want to go to high dimension to benefit from concentration of measures. But you don't want to go to too high dimension, because then the curse of dimensionality just unravels the whole situation. Because what happens is your spherical cap becomes too tight, and you have to go pretty far to find anything relevant. It turns out that in very high dimension, everything, even somewhat related things, may be somewhat close to the equatorial band. You don't want to go that. It's like, finding neighbors by getting into a pickup truck and driving an hour. You don't want to do that. So in between is a Goldilocks region of dimensions, which is this. And so it answers the question, why do text embedders pick a dimensionality between 100 and 4000? Is that really true? Let's go. The leaderboard that captures the best of these is a board called MTEB leaderboard. Let us pay pilgrimage to the MTEB leaderboard, because that's what most practical engineers do. They'll say, oh, we need an embedder, let's see which is the best these days. MTEB leaderboard, maintained by Hugging Face. And here we are. Now, we use embedding for many, many things. At this moment, we will look for search, retrieval. Performance per model size. But okay, before we do that, look at the embedding dimensions, guys. It is this column. What do you notice? 3840, 4096, 3072, 2048, 1024, 1024, 768, 768, 512. Remarkably, they are all in a narrow band. Either 100, like between 100 and maybe 600, 500 and 4000. Do you see that, guys?
There's a 32,000.
Yeah. Yeah. There. Let's go to that one. This one Do you say that it says grid? 8 cross 7b. They are taking 8 vectors and concatenating them. That's why it's looking like 32. Storage is 32. So it's not really 32 dimensional. So this is how you develop intuition into what goes on. Otherwise, it just looks like a mysterious number. What do I care how many dimensions it is? Dimensions affect your storage. The more the dimension, the more the numbers you have to store per piece of text. And so what happens is your storage blows up. Now you say storage is cheap, who cares? What's the counter argument to that? What's the counter argument to that? Compute cost would be too. Okay, so one hypothesis. Compute cost will be too high. Saurabh says that. What other hypothesis? Memory is limited storage. Memory. Oh, these days any self-respecting server will come with at least 2 terabytes of DDR RAM. Ah, says the infrastructure guru. Very, very close, but yes. The seek time. Seek time. Actually, the reasons are like this. It is the memory hierarchy that he talked about. See, computes that happen in the GPU are lightning fast. Computes that happen in the main memory, relatively speaking, are glacially slow. Computes for which you have to go to the disk and retrieve data and then do it, might as well wait for the next incarnation, next life to complete. Relatively speaking, they're very, very slow. So when you want to store the same, let's say 100 million pieces of text, and they don't fit into physical memory, their vectors don't fit into physical memory, you have to go to disk and retrieve them. It's very slow. The other problem that happens is you ideally want it to fit into a GPU memory because then they're lightning fast. Your searches are lightning fast. Here's a metric. In a social media company which serves a user semantic search at web scale, what is the latency accepted for semantic search? Given a query, what is the round trip latency accepted? 13 seconds, 15 seconds, and assume that there are 100 billion items there. 100 billion. Typically, pager alerts go off if it crosses a threshold of like 50 milliseconds. Right? Think about it this way. So that brings us to our next topic. How do we search across 100 billion vectors and find the nearest neighbors? That's what you are doing, isn't it? The bigger the vector, the more computes you have to do. Distances, computations become bigger. High dimensional data has a compute cost, a storage cost. But is there a way to shrink down the compute cost? Because if I have to compare it to every other vector, does that look sane? There has to be a better way to find the neighbors. How would I do that? Louder? Yes, you sort of bucketize it somehow. That leads to algorithms called approximate nearest neighbor algorithm. What it does is, and we'll talk, that's our next topic that I'll just touch upon. Today I'm just touching upon these topics. We'll go deeper into it the next time. See, when you go, let's say that you need to paint your house. Some part of the wall has chipped off. So you take a picture of the neighboring wall that is good, carry it on your cell phone, and you go to the hardware store. When you go to a hardware store and you're looking for paint, do you see a wall of cards, color cards there? You need to match it to something. What do? Let's say that your color is some shade of vanilla, cream color. Do you bother to even look at the deep red section, the deep blue section, the deep green section? You don't. You immediately go to the cream vanilla section, and then you closely match. What it means is, just looking at the data, you have already excluded or carved out a lot of the data that you don't want to compare it to. And you compare it only to a few of this. And that is only possible because you remembered that this is cream colored. So deep red, deep blue, deep green, all of those are excluded. All those greens, everything is excluded. In other words, the vector embedding space, you like, for example, a query vector comes. You know that it's going near the North Pole. You don't want to consider things that are already too far away. There are algorithms that help you do that. They all come under the category of approximate nearest neighbor algorithm. For this reason, approximate k nearest neighbor means you pick k of your neighbors. So these algorithms are called ANN, approximate nearest neighbor algorithms. We will cover this in a subsequent session in great detail, so I don't want to go into the technicalities today. But the broad flavor is they do exist. But here is what they trade off. They give you lightning fast searches. You don't have to do a linear comparison to find the nearest vectors. But you have to pay a price. You have to pay the piper. What do you have to pay? You have to trade in a little bit of accuracy. Usually the traded in accuracy that you lose. So suppose you get the top 100 neighbors. Actually, you might have missed one or two real neighbors, and you might have brought in one or two who are not really belonging to the top 100. But that minor error rate is completely acceptable. The error rate is typically not 1 in 100, but 1 in 10,000 or 1 in 100,000. So by trading in a little bit of accuracy, you gain a lot of speed. You can search through hundreds of billions of items, vectors, in the blink of an eye and find the nearest neighbors. There are many powerful algorithms out there. If you want to just search, I'll just throw the word there, look into FAS. What could FAISS stand for? F could be? Okay. AI, what could S and S stand for? Similarity search. That is it. Or semantic search. It is a industrial beast. Isn't it fortunate? It's all in the open source. And it takes 5 lines of code to use it. This will be one of your labs you will be doing. Lab. I hope you guys are getting excited about the labs that are coming. So to summarize, let's put the pieces together. You take all the knowledge that you have, give it to machine. Machine makes it machinese as points. Then, given a query, you just go search, find the nearest neighbors. Now finding the nearest neighbors has become extremely fast. You retrieve the answer, and that completes the story. And what you are looking at and what is born is semantic search. Now the question is, who does this approximate nearest neighbor search? You don't want to store these vectors in a relational database or in a traditional database. You need something that stores it smartly and can do approximate nearest neighbor search. Those beasts that do these two functionality store a vector efficiently and can be blazing fast in finding the neighbors of a vector. They have a name. Can you guess what that name is? Vector database. These are vector databases. Vector databases have been around for a very, very long time, decades. But with the coming in of AI and of language models, they suddenly assumed central importance. So there was a time in 2023 when so many people were going to VCs and saying, I have a brilliant idea. What is your brilliant idea? I'm going to make a vector database. And so there was a mushrooming of amazing new ideas for creating vector database that could do fast queries across huge amounts of data. Today, the vector databases that we tend to use, they're commercial ones and then they are open source ones. In the open source community, Qdrant is one, Chroma is another, VVet is another, Melvius is another, Melvius is another. And there are many such. And then commercial, of course, there's Pinecone, VectorDB as a service. Every single cloud provider is offering you a vector database. There are many, many vector databases. But for the sake of our course, we will standardize on Q. You might as well become familiar with Qdrant. Occasionally, we may use Chroma. For simpler situations, Chroma. But Qdrant has been production tested. It scales massively. So unless, if you were to ask our recommendation from the open source, we would endorse it. And we don't get any kickbacks for it. Kidding. So you can go with it. Why? The reasons will come to in subsequent sections. So guys, today has been a day in which we covered a lot of territory. Was it interesting? So we are done. We know language models. We know how to use them. Course over. There has to be a catch to all this. There is actually a catch. And that is where we'll go into BERT and go a little bit deeper. But for today, I want to keep it a relatively short. I want to use the last hour to answer questions and to take in registrations. Would that be fair, guys? We can go much further next time. But all of these ideas, don't be alarmed. There's not much of a problem. It means we need to improve upon what we have. Now, let us go back to our lesson plan and see, did we cover all the things we planned to cover? We said that week one. Oh, now you see why the cover is what it is? Does it remind you of something? Yes. So once you are looking at the stars and the sunrise, but the moment a predator appears, all of those things vanish. The theme today was, what does it mean for a machine to understand? Do we have a intuition towards that? Then let us look at what you must carry forward with you. Labs will reiterate these points and make it real. From this week, you need to carry forward the following messages. Articulate a working definition of understanding appropriate for machines. How do machines understand text? Convert it to machines as embeddings in a vector space. Right? Explain why semantic similarity does not require keyword overlap. Do you notice that nowhere did we use the keywords or dictionary, etc.? Describe how context reshapes meaning in language models. We understand the role of context. They help a word soak in from the context its full meaning. And because of that, you saw that in the search, in the lab, when we did the search for a friendship with animals, The first search results did not contain the word friendship or the word animals. There was no keyword overlap at all. But there was a very good alignment with the meaning of the text. That is it. Interpret, okay, sorry. Next is interpret attention as a mechanism of meaning preserving retrieval. Attention does that, right? It helps you get to the meanings, use that to create vectors that you save. In distinguish surface language behavior from internal representation. What does that mean? Two texts that mean, let's say, identical things, but you and I use different language to say, different words to say it. They should land more or less on top of each other or near each other. True? That is it. May I request you, we covered the paper, Attention is All You Need. There are two papers that we didn't cover. I leave it to you. They're easier ones, and they are the history of that. Efficient estimation of word representations in vector space. Before you did text embedding, there used to be word embedding. The precursor to it. And that's what that refers to. See if you want, if you get time, read it. It was the first time that you had a semantic regularities in language emerged at geometric structure in learned vector space. I keep saying this over and over again, but you'll realize that this field of generative AI, if you look at it as simple geometry, everything will look easy. Everything will look easy. There is an Oliver Twist list. Read it in that order that it is given. You'll find some things, but many of these things you can do over a period of weeks, but I just thought I'll mention it for you. Do we all have a copy of this weekly plan? If not, I have them here. Please come and take it. Anyone else who doesn't have, please come and take it.
As if it's not in the course portal.
Oh, it will be posted to the course portal.
Okay, thank you.
Yeah, I think Samantha or somebody in my team will do it.
Mm-hmm.
I haven't done it, but I can post it for today. Okay, switch. It will be there on the course portal.
Okay, thank you.
And those of you who are on remote, is there anybody on remote who is only on remote and is registering? If you are, send me an email. We'll email this to you so that you don't have to wait for. Samantha should be up actually in 1 more hour and she'll post it. But just in case. And for the rest of you folks, because there's a public talk today, it was hybrid. There are a lot of people from Meetup, our Meetup community who joined us. So I would like to thank all of you for joining this session. I hope you got something out of it. I hope you had fun. And I look forward to seeing you in subsequent meetups, subsequent events. At this moment, I would like to open it all up to questions. Questions, guys? Yes. No, it's like you're sitting at the North Pole. You're willing to go only up to the limits of the polar cap because you feel that anything relevant should be in there. Outside it are the irrelevant things. That's why. That's why you say, I'll only look at the polar cap. You do it, and how you do it, you'll learn. Questions? Yes? Okay. The question asked in the audience was, does the order of the sentence or the structure of the sentence itself matter? The answer to that is best illustrated with an example, which is also the title of a lovely book. One second. Look at this phrase that I'm going to write. Now, suppose I put a comma here. After eats, it eats, shoots, and leaves. That looks like something rather murderous. On the other hand, if I put the comma, the purple comma, after the word shoots, it eats, shoots, comma, and leaves. What are we talking about? A cute panda. So think about it. Just the placement of a comma makes such a difference to a sentence. What about moving the sentence around in a sentence, in a paragraph? Or what about making structural changes to the sentence? That would have a deep impact on the meaning. The beautiful thing is, language models are completely focused on understanding the meaning of the sentence. And whatever elucidates the meaning of the sentence, it will zero in on. Sometimes position does. Quite often position does. Any other question? It is not a matter of small models or large models. Dimensionality is an orthogonal concern. You pick a dimensionality that you like, and then from the last layer of the model, you produce a vector of that dimensionality. Having said that, generally, bigger models tend to produce better semantic understanding. That is the neural scaling law. We'll study the neural scaling laws in subsequent sessions. No, given a vector, vector belongs to, what just happened? Vector belongs to some dimension, let's say 1000. So a vector will just be an array of 1000 numbers. So here, guys, I'm addressing an audience question for those of you who are remote. And again, to remind you, guys, please try to turn on your microphone so that the remote people can hear questions. The question asked is, how does the dimensionality of the vector relate to the size of the model? They're completely independent concerns. Dimensionality just refers to last layer, what dimensionality you have, how many neurons you have at the last layer. You can have a very tiny model with with 1000 dimension last layer, or you can have a ginormous model with 1000 neurons in the last layer. These are orthogonal to each other, independent axes. Having said that, it is also true that there is such a thing as a neural scaling law. What people have found is that bigger models trained with more data and more compute tend to produce better semantic understanding. They are better language models. Does that answer your question? Yeah. Next question. So should we take a 1 hour break and come back for the next session for the next 3 hours, or go home? All right, guys. So ask questions. I want to, okay, I'll quiz you guys. Can I ask you guys questions? Okay, I forgot to bring my jar of candies, otherwise I throw candies. So inherently, this is a thought question. I said that machines speak machinese as points in a vector space. Why do they think of thoughts, language as points in a space? Why it makes sense to think of it like that? That's one answer. Say that again.
Is because the more relevant thoughts are closer together and the less relevant ones are further away.
Yes, in other words, it naturally supports proximity. Semantic proximity means literal distance. Yeah. So semantic proximity becomes literal distance proximity because points, you can, in Euclidean space, you can compute the distances between them. What other reasons could be there? Microphone. Guys, please do use it. Otherwise, people who are on remote, they find it very unfair.
It's easy to do mathematical calculations on.
It's easy to do mathematical calculation. What sort of calculations would you want to do?
All of the things which we discussed.
Yes. See, machines learn. They learn through a process called gradient descent. And what it means is that in the beginning, when the machine doesn't understand language, it will put points randomly somewhere. But gradually, as it is beginning to get a sense of the language, it flows unrelated things away from each other, and it flows things that are semantically similar towards each other. To flow, you need a continuous movement. Words, what are the infinite number of points between cow and zebra? No, it's a discrete space. Texts are discrete space. Linguistic space is discrete. It is hard to learn in that discrete space. But if there are points in Euclidean space, gradient descent, you can actually smoothly bring similar things as you learn about human language, bring them closer to each other, and dissimilar things, you can keep separating them out smoothly from each other. So smoothness, continuity, differentiability, those all are necessary ingredients for a neural network to learn. And that is why a point representation is the most intuitive representation of a thought. Now, people, I keep saying point, 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 but people will say, okay, but it's a vector. A point is a vector, and we talk of vector databases. What's the relationship between the two? So I'll give you an answer, and then one day I'll take it back. So this is a answer that typically can be given. Any point in coordinate space, Euclidean space, so suppose you have a point P. I can connect point P to the origin. Now, what is a vector? Vector is an arrow with a magnitude, a length, and a direction. Does this now have both length and direction? Right? You connect you consider the tail implicitly to be the origin, you consider the head to be at the point. Therefore, this point can be represented with x1. Let's say the axes are x1, x2, x1, x2. You can represent it like this, two numbers. That's it. So people use these two words interchangeably. But I'll leave you with a cryptic remark. I'm saying point and vectors, therefore, are synonymous. For now, they are synonymous. But one day I'll take it back. Yes. That is it. Of points. That is it. With ANN, see, you. No. So the question was, so vector database is just a vector database of these arrays or numbers. The answer to that is true and false. That is what they store. But the magic is in how they store and how they can lightning fast give you the nearest neighbors. In other words, the storage is not so much important. It is a helper to make this approximate nearest neighbor algorithm possible. So you can say that vector database, more properly said, are ANN implementations, high performance ANN implementations. That is the right framing of a vector database. Any more questions? How many of you feel that you got some sense of how language models think, language models understand text? Raise your hand. Okay, some of you. It will come, guys. Today was just framing, giving you the big picture. The first lab will also be relatively straightforward because we have to give you VPN access, user accounts, and blah, blah, blah. Oh, by the way, that is only if you have bothered to register. If you feel I showed up in the class, therefore I'm registered, that might not work with the TAs. Yes. If you are a past student, then it is free. That's one of the features of our course, guys. You don't have to understand everything in one go. You can always come and repeat the course. And repetitions are free.
Is that recorded? So all these classes which you have on Saturdays, is that recorded? Like, can we listen on Sundays? Stuff like that?
Oh, of course. If you miss a class, no problem. Everything that I said is being, see, this is being recorded. So everything is recorded.
Great.
Don't have to worry about that. Ida, very good question from the audience. This time, do we have to form teams? Teams are optional. You can be a lone wolf, or you could form teams. Whether you do a team or not is up to you. Generally, I would recommend that if you are an individual contributor and you feel pretty strong about your abilities, be a lone wolf. We will not put restriction on that. You just become a one-man team. You will get the same GPU access. On the other hand, forming small teams is motivational. You make friends, you make progress. And frankly, you get those rooms only if you form teams. Think of it as free WeWork. Next question. All right, folks. So if there is nothing else, I will.
So what is going to be on this Tuesday and Wednesday?
Oh, that is Chandra will lead. Tuesday will be a recap.
Same.
What we do is my TAs will sit and listen to the whole lecture, and whatever I said, they will by hand take notes and screenshots from here and put it into a document. That recap a lot of people find very useful, and they carry with them as permanent assets, because video takes a long time to watch. They just read the recap, and the experience from previous cohorts is those recaps have proved extraordinarily useful in job interviews. And people keep it on their desk when they are doing projects at work. They do that. But if you feel you understood everything here, what you can do is you can skip that session and watch the video later at 2x the speed. The other thing in that session is the quiz. Quiz will be released immediately, like in a day or two. They will announce the quizzes there. You can take the quiz as many times as you wish, but at least take it once. It will be not only a reality check, but you'll learn from the quiz. The second lab on Thursday is much more important. All this theory must be boiled down to actual code. Now, first week will be gentle, like small exercises. So, but you need to get your feet wet and start doing something real. And that's what that Chanda and his team will take you through.
So this time around, setting up and all those things, is it part of the, that's
Thursday.
Thursday, okay,
Lab
okay.
code. The second lab. Say that? Something on Wednesday. Let's go and see what is there. Wednesday and Thursday. Yeah, Wednesday is a recap. Oh,
Wait,
no,
is
not
Wednesday the recap or Wednesday the first lab?
Okay, let's look at it. Wednesday is the recap. Thursday is the main lab. The labs are all over Zoom. The only thing in person is this session. Yeah. I know. The reason for that, guys don't require it, is Bay Area traffic is the loveliness that it is at 7 o'clock on work days. It's a very harsh commute for people, so we don't require that it should be in person. Nothing is in person. Only Saturday session is in person. Sunday is agent. That also is in person. No, see, for you guys, only Saturday is in person. For other people, there are other days in person. Context matters. Exactly. Very well said. Context matters. Oh yeah, you can come here and sit here and do your labs, but I don't require you to do it. Yes, that is right. So Sangeeta and her has, for example, and her team, they would always come here and do their labs, because then you get to talk. Guys, these rooms you can use. Collaboration really amplifies your learning.
So will there be anybody over here? I mean, other than your team? Will you come?
Yeah, of course.
Yeah, okay.
Somebody will be here. But I hear that there are some ghosts also there. No, I'm kidding. After the class of over there's a 2-week grace period. You have that. That's why I said the course is actually 14 weeks. The TAs will be helping. See, what will happen is you won't finish your project in 12 weeks. You'll need some grace period to finish it all. And so you get 2 more weeks. After that, do you guys remember the story of Cinderella? What happens at midnight? The carriage turns to pumpkin. So your cluster will also turn to pumpkin. You'll automatically lose access. Any other questions, guys? All right, in that case, I'll end the formal session. Those of you who are registering, please stay back and come and meet me.